his PhD from the National Center for Radio Astrophysics, TIFR, in Pune, and alongside with, which was at that time used to be associated with also Pune University for the PhD degree in 2000. Then he held 2 postdoctoral fellowships. One is NOVA Fellowship in University of Groningen, Captain Institute of Astrophysics, and then for 2002 to 2004, and then he was a Jansky Fellow from 2004 to 2008 in National Radio Astronomical Observatory in USA. He mostly works on, he's obsessed with fundamental constants actually, and he works on the evolution of these fundamental constants and the astronomical probes of these fundamental constants essentially, and galaxy formation, evolution, high redshift galaxies, interstellar medium, and many other things. Yeah, so Nisim, and the floor is yours. We cannot hear you. We cannot hear you. Yeah, it's a mime show. Sorry. Something is going wrong there. Still, we can't hear you. Maybe the main audio settings somewhere, the input mic somewhere went wrong, probably. Still no sign. No. Can you hear me? I guess. Okay. Yeah. Okay, fine. Then, yeah, something is wrong at your end. Can you quit the meeting and join again? Probably that will work. Just press the red cross. Yeah.
He's saying now it is not letting him join the meeting.
Okay, he joined for momentarily in between. I think then again the moderator or the host has to allow. But yeah, I don't basically. I don't have that ability. Maybe, yeah.
कर रहे हो
Can someone from MPCST check?
Yeah, Bhupesh ji, आप या कोई और is there to help?
Can you please check, because yeah, now Nisim is again in. Let us see. But hello, Nisim. Can you hear us now? Yeah, we heard you momentarily. Then you're.
Can you hear me now?
Yeah. Now it's clear. Now
Okay.
yeah.
Yeah,
So it
so-
is working now. So
Okay.
please start your talk as long as you. Yeah.
We'll try it again.
Yeah.
Can you hear me now?
Yeah.
Yes.
Okay, so we'll test it at every step of the way.
Yes.
Can you hear me now?
Yes, it is working.
Hallelujah. Okay,
Right.
fine.
Okay,
So I'm
fine.
very sorry, everybody, for all the chaos. This is partly my fault and partly WebEx's fault, but I hope it's mostly WebEx's fault. Okay, so let me, unfortunately, since I've eaten up much of my time already, let me start with, let me get right down to it. I'm going to be talking to you about astronomical spectroscopy.
Hello, you are inaudible, Nisim. And who is Anil Jaishwal? Could you please mute yourself, Anil Jaishwal? Could you please mute yourself? Because I can hear some sound from. Yeah, now it is muted. Nisim, can you speak again? Yeah, I can see some basically waves in your mic, but I can't hear you actually. Yeah, increase the input volume. Still, I can't hear you. No. It's something going wrong. I don't understand what it is actually. And as I'm not the host, I really don't have much. Okay, maybe. Yeah, no, we can't we still can't hear you actually. No, we still can't hear you. No. It is annoying. Still can't hear you. If you are speaking right now with your video off. Yeah, I guessed that. Okay, still can't hear you with your video on. I am trying to see whether actually at least I can see some sort of input in your mic here. Some waves are being created, but that is not being transmitted to us. My volume is maximum. I guess all the other audience can also cross check. Can anyone hear Nisim by any chance, or it is my speakers or headphone?
No, sir, we are not
No,
audible. No, sir.
no, they can't hear you. Okay, so it's something is happening at your end. Let me check again. No. Yeah, I really can't do anything from my end.
Yeah, I've requested to make you a co-host, one, and then.
Okay. Because
and then improve things.
I can't see anything from my end. There are certain basically flashes of audio wave. No, it's not working. No, not working. So okay. So right now, Nisim, I can't see the mic option just beside you. Okay, you can't hear me. Can Ovirup hear me?
Yeah.
Okay, so then uh, if you are okay, Nisim, can you just as a yeah, if you can use some sort of earphone with mic, that might work. That is somebody suggesting. If you have something of that sort, because I can't see the mic symbol beside your name right now. Okay, okay, so that's a problem. Uh, Okay, Nisim, just to try, if your Firefox is updated or the Google Chrome, it was updated recently. Okay,
We
okay,
can see you, we can hear you, we cannot hear you. Sorry.
we can't hear you. Basically, the mic symbol besides you. Okay, he disappeared. Let us. I think it is due to the. He said he is using Chrome. The Chrome generally WebEx doesn't work that well in Chrome actually. I am using Firefox. That's why.
So he's using Chrome. I also asked you to make you. So Ravindra Kodav, are you there? You seem to be a
Basically,
co-host.
yeah, I will just ask Nisim to use maybe Firefox.
That's
Let's.
fine. Ravindra Kodav, your name is on. You are a co-host of this event. Nobody's answering.
Yeah, that.
Will you hear me now?
Yeah,
Hello.
yeah. Hello, Nisim. Yeah, it is extremely loud. Now I can't hear you.
Okay, that's because I wasn't saying anything. Is it okay now?
No. Now it's clear.
Perfectly fine.
It's fine? Okay, fine. Well, let's try it again. I will admit that this is driving me completely insane.
Yeah.
The worst case scenario can be you can send your slides. I can play next from here, and you can.
Yeah. I can do that as well in the worst case scenario. Yeah.
Let's see if this thing works now.
Yeah.
Yes.
Can you hear me now?
Yes.
Okay. Next step. Can you hear me now?
Yes.
Okay. Next step.
Okay. Let us not go full screen then.
Yeah,
Maybe
yeah.
that is the trick.
Yeah,
Okay.
I think you can just minimize the sidebar.
Yeah, just on the right hand side, this editing bar that is, if you, yeah, nice.
Oh God.
Okay, okay. Yeah, I think we can live with this one. It's fine. It's readable. Means everything is legible, so it's
Yeah,
fine.
fine, perfect.
Yeah, please go ahead. Yeah. Yeah. So everyone else except Nishim, please mute your mics. Hi, Nisim. Can you say something? Are you still there? Yeah, now it's gone again. I'm sorry. Shit. Sorry. No, I can't hear you. I'm sorry, I can't. If you can send me your slides, I am also on Linux. Probably, if it is Open Office, I can open it here and share the screen. So then we can try basically keep you in only in the audio mode, and you can just instruct me. Like the old times, I will change
so,
the.
Suman, you're now the co-host also.
Okay, fine. But I can see Nisim's mic, but it is not receiving any sound input. That is what it is saying, because there are no waves being created. Okay, okay, fine. So, okay, if you have sent me the, let me check my email. If you could send me your slides, I can just share it from here, and you can speak. Probably that would be the best way out right now. Okay, fine. We can't hear you anyway. I am just trying to
He has
see.
already sent it.
Okay, where? I have not received it actually. No, it's not with me. Maybe it was sent to you by any chance? Ovirup, can you forward it to me in case it was?
I'm checking.
I haven't received it yet.
Me neither.
Okay. It could be also, but it is unusual because the video is working fine. But why the? It's really unusual. I have never experienced it.
It almost never happens here. That's it.
Yeah, it's an unusual thing.
No.
No, okay. I haven't. Are you? Yeah. Sorry to ask you. Are you on a stable internet connection right now? So sorry. Yeah. You must be because I can see your face. Yeah. I have no idea what is going
So,
on.
Nisim, if you can email your slides to either me or Suman, that will be okay.
Yeah, maybe just as a reply to the last email that I sent you. Maybe, yeah.
Yeah. Okay.
And then we can. Yeah, I will try my best. And maybe you just have to switch off your video just to
Did
make.
you receive the? Did you receive Suman the slides?
No, not yet. Not yet. No.
Okay. You can put it up on Google. One more step.
Okay. I don't have the Google Drive's access, so you have to give me that.
No. There is no Google Drive as
Oh,
of
okay,
now.
okay.
I mean, he can just share as a Google Slides and to you. And you
Okay,
can
yeah, that is also fine. That is also fine. Yeah. In any mode, it works.
Sorry about all this. It is
Yeah, and
unprofessional.
I have just one request, Nisim. Can you try, because right now you are trying with Google Chrome, right? So if you try with Firefox, it might work. Right now I am co-host, so I will be able to let you in if you quit and then try to join, because I am
Okay.
using Firefox.
Suman, it is there with you right now.
Okay, fine. Yeah, I got it. Just let me download it. Yeah, it's here. And yeah, downloaded. Let me open it. That's all. Right. Perfect. So now we will go to that one. Share screen. Share screen. Windows. Select window screen. Allow. Can everyone see the slides?
Yeah, I can.
Okay, perfect. So once Nisim joins back again, then maybe he can stay on the audio mode only. And let us see if it works.
Okay. So,
No, I don't. Yeah. Hello, Nisim. Can you hear us?
I can hear you now. Yes.
Yeah.
Just start speaking.
Sure.
Ovirup, can you switch off your video? Probably, just to make sure that things are, kind of stable. So, can you see your slides right now?
I can see my slides. Yeah.
Yeah. So, please go ahead. I will change them. Whenever you need to change the slide, just tell me. I will change them.
Okay, sounds fine. And are you opening them in LibreOffice or in?
Yeah, it is in LibreOffice.
Okay, that should be fine. I hope movies and so on will play, but that's okay. Yeah, great. So lots and lots and lots of apologies, everybody. And unfortunately, this talk is already turned out to be a disaster.
Well, we lost your audio again. I'm sorry. Shit. So, I'm really sorry. Yeah, if I really don't understand. Now you have changed the browser as well, so I don't know what is going on.
I think there is some issue with the machine over there. Maybe it is kind of interrupting.
But the video is coming on nice. Maybe the
Yeah,
audio
video is
input,
coming on nice. The voice, the audio is
audio input has some sort of.
some sort of an issue. Yeah, it switched
Okay.
off.
Okay.
No, I think browser is fine. Browser once
Browser
it
is
connects,
also
it
working.
cannot. Yeah.
Okay. Fine.
Okay, I think then what we can do, it is I agree with you. It is really 3 o'clock, and you also rush to something. And I think what we can do, Nisim, is that we can try out in a evening time with any WebEx. Okay, because I think MPCST is using WebEx platform, so we cannot change it. But me, you, and Suman can test it out tonight or tomorrow night, anytime with WebEx. We have other ways, and just see between three of us if it can be done, and maybe we can do it at off peak hours, or maybe early tomorrow.
Yeah,
Yeah.
Now you are back again. Hello, Nishin. You said something, right? No, you are not audible. Sorry.
uh,
Yeah. Okay. So I think maybe we can resort to that. Let's not panic, and it's okay. It happens. I mean, there are so many.
Aviroop, if you want, I am ready.
Yes.
Okay.
We may be switching to you, sir. Yeah. Thanks. Yeah.
Yeah.
So Nisim, I think what we'll do is I think either me or Suman can send out a WebEx request something around 9 p.m. today, and we can just do it this among three of us. And if everything goes well with your settings and everything, then maybe we can just have your talk early tomorrow, say 1:30 to 2:30, something like that. 1:30 to 2:30 tomorrow. Yeah, tomorrow, not tonight. No,
No,
not tonight. Yeah,
not tonight.
no. So let us see. Let us see how it goes. Play by the ear and see how things shape up.
Yeah.
Absolutely sorry. I mean, we never.
Yeah, we are.
It's WebEx is one of the most stable ones. So absolutely sorry. Sorry, if, all the students who have joined. We'll make sure he comes back. We will not leave him like this. He will come back. So yeah, thanks. Bye, Nisim.
Yeah, really sorry. Bye.
Really
Yeah.
sorry. Yeah.
So, Professor Ram Sagar, will you be willing?
Yes, I am ready. So
Okay.
you give me green signal, I will start.
Yeah. Please
So
go
you
ahead.
can please share your screen. Then I will introduce you, and then you can start your talk.
Right.
Thank you.
Okay.
Thank you, sir. Just give me a second. If you could share your screen, sir. Yep.
Yeah, I am doing that.
Okay.
Is it visible now?
Yes, yes, it is visible. It is visible. Thank you, thank you. So you can go into the full screen mode. Then I will introduce you. Yeah, presentation mode, sir.
Yeah.
Yeah,
Is it visible?
Yes, yes, it is perfectly fine, and you are audible as well. So
Thank you. Thank you.
just let me introduce you. So we have with us Professor Ram Sagar, who is an ex-director of ARIES Nainital. You all know about this particular astronomy institute. ARIES has one of the optical telescopes on campus, as well as one of the state-of-the-art optical telescope in Devasthal, up in the mountain. So, Professor Ram Sagar did his MSc from University of Gorakhpur in 1973. Then he did his PhD also from University of Gorakhpur in 1981. And he has been associated with ARIES for a very, very long time. And his main research interest is star formation, stellar evolution, star clusters, gamma ray bursts, active galactic nuclei, astroseismology, and gravitational lensing and atmospheric physics. So, Professor Ram Sagar, the stage is yours.
Okay. Thanks, Dr. Suman. Good afternoon to all of you. Thanks for kind introduction. I am thankful to the organizing committee, Professor Avrup Datta and Professor Parihar, for asking me to deliver this talk in the second winter school on observational astronomy, organized jointly by Madhya Pradesh Science, Council of Science and Technology, IIT Indore and IIA Bangalore. I am happy to note that MPCST has taken number of new initiatives and started collaboration with other national academic institutions like IIT Indore and IIA Bangalore, etc. Based on my experience in Nainital Observatory, where I served for almost 18 years under state government as well as central government, I have no hesitation in stating that the new initiatives taken by Madhya Pradesh CST will provide boost to the upcoming Dongla Observatory located not very far from IIT Indore. Now let me come to the topic. Today I'm going to talk to you regarding what are binary stars and variable stars, and why they are important in astrophysics. So basically I have provided few headlines which I will be telling you during my detailed presentation, one by one, slide by slide. Please feel free if in between any student want to ask any question, I do not mind, because my aim is to communicate with these young students. So to begin with, while we talk about astrophysics and stars, HR diagram or Hertz-Russell diagram is like a periodic table in the area of physics, where chemistry rather. And in this period, HR diagram, if you see, y-axis is absolute magnitude. In other words, it's the luminosity, and x-axis is the spectral type, and the top of that it represents temperature of the stars. And as you can see, a very large fraction of the stars, they occupy what we call main sequence stars. It means at the center of these stars, hydrogen burning is on, and then they evolve to the various phases of stellar evolution. And if you see, in fact, the main sequence, there is a very well established mass luminosity relation. In fact, luminosity is 3.6 power to the mass, and the range in mass, minimum mass generally, it depends upon the model. It is 0.1 or it can be 0.0607, also solar mass, and maximum about 120. This upper limit is also debatable. It depends upon the models and the type of information we have. Most of the mass what we measure considers solar mass as a single unit, which is number wise, it's a 2 into 10 power 33 gram. And luminosity also, most of the time we are talking in terms of the solar luminosity, where 1 unit is 4 into 10 power 33 arcs per second. Now, why we study star? Because you have heard a number of speakers before me, and from them you must have learned one thing, which we call, mass is a very important parameter in stars. In fact, mass dictates the life of stars and future path in its stellar evolution, that what will become after its death, whether it will become white dwarf, it will become neutron star or white dwarf, finally, white dwarf, neutron star and black hole, all those things are dictated by the mass. And mass of a star can only be measured directly by observing effect of the gravity on another object. And this is most easily done for 2 stars which orbit each other, and that's what we call binary stars. If the 2 stars which are formed together, they are definitely, generally they are formed together. There are various ways of formation, but the most popular way, and which I will be talking today, it's the process of star formation. I'm not going to talk about dynamics, where if the 2 stars come in a cluster very close to each other, they can also form binary. So that aspect I will be not talking about. So again, how we derive this mass, here we use very elementary principle of, what most of you must have studied in your high school and intermediate physics syllabus, what we call Newton version of Kepler's third law. And this states that if 2 are objects, star A and star B, having mass m1, m2, ma, mb, which are denoted here, and the third law of its state that their period p and the separation between them, which is denoted here a, they are related by this equation. So if we can find out orbital period of these binary stars and distance between them, then we can find out what is the total mass of the system, that is mass of A and B by this relation. That is, the sum masses can be found, that is m1 plus m2 in solar units. If we measure separation between them in the unit of astronomical unit, which you might be knowing by now, that it is the average distance between sun and star. In other words, if you convert it to the terms of light seconds, then it takes 500 seconds approximately, to reach. And the speed of light is 3 lakh kilometer. So if you multiply 3 into 500, that's the average distance between them. And P period, if we measure in terms of year, then if you put then we can find out what is the total mass of the system M1 and M2. And that's where binary stars are very useful and helpful. And these, while they are evolving, the center of mass becomes the point around which these stars revolve each other. This is a picture which showing orbits and mass of the binaries. As you can see, this orbits this way, and the red one, which has a smaller mass. This is a typical example where m1 by m2, that is ratio of the 2 object, mass ratio is 3.6, and ellipticity of the orbit is 0.4. And this, as you can say, this is the center of mass M2 is denoted at a distance A2 and M1 is denoted at a distance A. So that if that is a system, and then this is one system which was observed with this mass ratio, and if its period which was found roughly about 10 years, and the mean separation, if it is measured in terms of the average distance between Sun and Earth, then 6 astronomical unit, then the Kepler's third law tells that the total mass is 2.16 solar mass. And that's how we get the sum of the masses. Here, one thing is very important, that to find out this orbit, as you can see from this telescope, they are able to see both the stars separately. And that is very important. And also you are able to see how they are moving. For example, in 1984, this was the place, 87, it moved to this place, and so on. So that's how you find the orbit from their location in the sky, because these stars are located on the celestial sphere. This is the example in a more detail, which is shown here, that how these stars, if they are visual binary, they are called, then this thing happen. But unfortunately, such objects which are visible to our naked eye, they are very, very small in number. In fact, not even 1% of the total binaries known even in our galaxy. And that's why this statement is correct, that for most of the binaries, one cannot separate the stars even with most powerful telescope. For them, we need other ways of finding out information about their orbital period and distance. And that's what is called spectroscopic information. And this reason why, for a large fraction of the stars, binary stars, we are not able to see. Because as you know, if you keep two objects at certain distance, then the angle formed by those two objects on our eye, it depends upon their physical separation divided by the distance. So as you know, most of the astronomical objects, they are located at a very far distances. So distances are large, and that's why even if they are separated, let us say nearby, if you put them 1,000 times, more distance than where they are visible today, their angle will reduce by that factor, because it's a linear separation divided by the distance. And it is the distance, enormous distance of these stars, which prohibit us to get, visual binary things in our picture. So let me explain you how people have, tried to do and why they call it spectroscopic binary. You take example of this AB, it's just to illustrate, the point. Star A, light is coming towards, it's moving, this way. So the light from A, it looks like it is approaching to us, and light from B, it looks like it's receding from us. So stars orbit each other, produce spectral lines with Doppler shift. And in that case, Doppler shift tells us that the objects which are receding from us, light from that at a particular wavelength, it will be red shifted, while the light which is approaching us, those spectral lines, they will be blue shifted. So as you can see, if suppose this was the mean wavelength of this line, A is blue shifted and B is red shifted. So this is the separation between those two lines. If you take the second example, all the star circles their orbits, the spectral lines move together. And in that case, as you can see, the separation between A and B, it has reduced now. Now, if you see when they become, aligned along our line of sight, and the motion becomes perpendicular to us, then it means there is no blue shift and red shift. Because of that, both these spectral lines, they merge together. So as you can see, A plus B, they coincide. When the star moves perpendicular to our line of sight, there is no Doppler shift. And this third case represents to that. Then they move further. So in fourth case, spectral lines shifting apart and then merging as a sign of spectroscopic binary. And if these changes happen, for example, in fourth case, now the spectral line arising from B, it is blue shifted, while the spectral line arising from A, it is red shifted. And this separation increased in the case of fifth, which is displayed here. So even if we are not able to resolve stars, we are able to observe their integrated light. This that when we have, let us say, 5 magnitude or let us say 10 magnitude stars, and if both have equal brightness, let us assume that A and B, they have equal brightness, they have equal surface temperature, means their spectral type is the same. Integrated light will be brightened by 0.75 magnitude. This is just from basic definition. So the integrated light becomes 9.25 magnitude if these conditions are satisfied. But if we take spectra, then depending upon the location of these individual stars, spectral lines will be shift in spectral line, that is separation between the spectral lines, that will change. And that is a signature of that it's a binary system, and that's why we call, since it's indicated by spectral lines, it is called spectroscopic binaries, because we cannot see them visually. So the total spread, that is size of the Doppler shift, gives velocities about center of mass. In other words, we can find out orbital sizes. The time to complete one repeating pattern, cycle, it is called period. So if we know P and A, then as it was discussed in earlier slide, we can find out total mass of the binary. This is third type of system. In fact, they are called eclipsing binary. You must have heard that sometime, in our solar system, there are occultations happen, eclipse, solar eclipse, and lunar eclipse, they are very well known. And the region. So similar thing happen in case of eclipsing binary. In the case of spectroscopic binary, you see, they were not eclipsing or occulting each other. But if their orbit is such that, you take the light from one star, it gets occulted, then you just see the shade. When they are not, in the line of sight, then you find a steady light. Again, in other case, the blue star is, eclipsing the other. So as you can see, and the pattern repeats. So this time is spent between this and this, it is called orbital period. And in fact, it depends what type of primary and secondary are these two stars, M1 and M2. The eclipse light curve, it provides information. So from the duration, we can find out orbital period. We can also find the size of the star, that how long it was. For example, in this case, you see it's very sharp dip. In other case, you see we have different type of star combination. Here, it's a stable, but depending upon what is the size of the secondary, your duration as well as depth and the way it dips, all these things provide valuable observational information which astronomers use to find out orbital period and separation between them, and so on, and hence they are able to find out stellar masses of the eclipsing binaries. Now let me just spend few slides which you might have seen earlier, or it may be repetition, but just for completeness, I am just showing you how these binary stars are formed. Their formation process, which I told you, it's just like a star formation process. So I am showing you these two examples. This is very young cluster, M16, and this is HST image, molecular cloud, and that's why we call it as a star forming regions. And in that, these giant molecular cloud on which there is a thousands, their number is thousands in our Milky Way, are enormous complex of dust and gas, sufficiently dense to be self-shielding from the diffuse interstellar matter, interstellar ultraviolet radiation field. Typical temperature, they have about 15 degree. Volume density is 100 to 300 particles per cubic centimeter, and masses, they range in the unit of solar mass, 10 to power 6. The low temperature and high densities and the presence of solid particles known as internal dust, they form, in fact, act as a catalyst and favor the formation of molecules. Thus, most of the giant molecular clouds, they are in the form of H2 rather than H1. Dust makes up the material, and it is the dust that renders cloud, attenuation at the visual wavelengths. And these are some typical parameters which are given for these things, that as the density increases, the mass decreases, extinction also changes. So these are some typical numbers which are given in this slide. But maybe this slide will explain you what I'm trying to tell you. That from these molecular cloud, as you know, instability equation which has been derived by genes, and if molecular cloud have mass larger than the gene's mass, then this molecular cloud collapse, and in fact it fragments, it breaks into smaller pieces. So it means your these numbers, they changed because the gene mass is depends upon the temperature as well as density. So if you put these typical numbers, then gene mass for diffuse hydrogen cloud, it's a 30,000 solar mass. In case of dense core of a giant molecular cloud, where temperature reduces 10 degree, typical order, density increases, gene mass decreases. So in fact, that's how the star clusters, this one fact you might have heard in earlier talks, that the probability of formation of individual star is extremely rare. There are hardly physical conditions in our galaxy or known molecular clouds where formation of single star. They always form in groups, and that's why they are called star clusters. And a good fraction of binaries, about 15 to 20%, they form in this process, and what we call, these are the primordial formation ways of binary stars. So the initial free fall collapse of the parent molecular cloud, it happens, then cloud fragmentation takes place. It leads to a range of stellar masses, formation of a protostar core, and once this protostellar core is formed, the star appears like collapsing on its own. It becomes independent of environment for a long time. And these are various processes, and these things happen, what we call this entire phase 1 to 5 as a pre-main sequence phase. As you know, in the main sequence, we have hydrogen burning started, but as you know, to start nuclear burning at the center of the star, you have to have, for example, temperature of the order of more than a lakh of degree Kelvin. Pressure has to be very high compared to these things. So in a strong, large temperature and in strong pressure, this hydrogen burning takes place. And that's where we say that zero age means sequence. In a sense, age, whatever we determine, it is when it starts hydrogen burning in its nucleus, we call it zero age. So that is called zero age main sequence. And these are some various stellar evolutionary path which has been described here. Hayasi track, how stars formed, and then it goes to main sequence. These are theoretical models which are done, and various physical processes which takes place on the way. For certain time, star is fully convective, then radiative core develops, and finally hydrogen burning starts when it reaches to the main sequence. Once it reaches to main sequence, then when hydrogen burning exhausts, depending upon the mass of the star, they follow various paths in the HR diagram, which are displayed here, what we call HR diagram. And these are called theoretical evolutionary tracks. These are model simulated things. And in fact, this is a typical picture of a star where you can say in the core, the nuclear burning, in the beginning, hydrogen converts into helium. Then it goes to the giant or supergiant phase, depending upon its mass. Then helium burning starts in the core, and so on. So these are typical picture where you can see that core, then radiative zone. For example, in case of our sun, we have photosphere, and where you have conductive zone. And you must have heard yesterday, day before yesterday, I think, from Professor Dipankar Banerjee about various activities happening on the sun, and so on. Now, how their stellar evolution, while we say it changes with time. What is the reason for changing? These 4 or 5 equations which dictate what we call stellar structure. One is what we call equation of mass continuity. If suppose dm is, this is a star, and this dm is the mass which is located at a distance r, then dm by dr is given by this equation. And then we call it hydrostatic equilibrium, because as you know, the radiation pressure will try to push it out, but gravity will try to push it in. And if you find out a balance between them, that's what we call as a hydrostatic equilibrium, pressure and gravity balances. Then, these are this is equation of energy transport. They are given in different ways, that where dl by dr is equal to given by this equation, where J is the rate of energy release per unit mass by all processes. If we take simple model in static model, then this is only nuclear burning which comes. But more generally, if the layer of the star is expanding or contracting, as you must have heard in earlier talks like supernova explosion or any other type of explosion, then this energy is not only nuclear but gravity, where the second term is negative if the star is expanding. And we can work it out, various things, and we can find out and that how these equations are tackled. And if you solve them together, in fact, that's what we call, so we have 5 coupled differential equations describing the run of mass, pressure, luminosity and temperature within a star with radius r, the distance from the center of the star as the independent variable. Note that the first 2 equations describe the mechanical structure of the star, while the last 3 describe the energy and thermal structure. The equations are coupled to each other through the fact that for a general equation of a state, P is a function of both density and temperature. Anyway, if you solve those things, then these are the tracks, flashes which have been showing. For example, this is our sun. Presently, we know that it's where hydrogen is getting converted into helium. Then it becomes red giant phase, and so on. If we have a 5 solar mass or let us say 10 solar mass, then the path followed is different, and different stages of nuclear reaction which is taking place, it's indicated on this. And if it is very bright and it's an evolved stage, that is helium burning phase or carbon and oxygen burning phase, we call it supergiants, giants, and in this process also you will find horizontal branch, asymptotic giant branch. And after this, if the mass of the remnant, whatever is left after supernova explosion, if it is less than Chandrasekhar mass limit, then it ends as a white dwarf. If it is more than that, then you know that electron degeneracy pressure, which was holding in the case of white dwarf, it is no more sufficient to hold the gravity. In that case, neutron becomes the second particle uh, due to degeneracy of neutron. You know, star gravity is hold, and in those type of objects, we say it's neutron star. If even mass is more than that, it means gravitational pull is stronger, then that degeneracy is also not able to hold, and then it becomes black hole. And that's how I can say the evolution of single star. In case of binary star also, for a large fraction of time, whatever I am telling about the individual stars, it holds good. And that's how does stellar evolution proceed in binary system? That was the main aim of showing you these few slides just I displayed. If the distance between them is large, then the star in the binary system evolve essentially independently, just like a single star evolution. But if A is not small enough, then as you see in the neighboring diagram, when a star becomes, go to red giant phase, or in giant and asymptotic giant branch or supergiant branch stages, then it expands. Radii becomes very large and temperature reduces. In that case, its evolution depends. When A is small enough, then a star can interact with important consequences for subsequent evolution. In fact, some of these astrophysical examples I will be showing today, which has been used in some astrophysical cases. So stellar evolution of binary system, if you see, it depends upon what the combination of those binary, primary and secondary. It could be, let us say, main sequence. It could be main sequence subgiant branch. It could be main sequence AGB branch, and so many combinations can be formed. It can be even, I will just describe, this is one of the burning, I will say, frontline problem in astrophysics, where people are trying to understand what is the progenitor of blue straggler stars or blue lurker stars, how they formed, and today's indication that these are the evolutionary effect of stars, where one is main sequence and other is white dwarf. If you go to the compact binary system, I mean, that's what is shown here. That I will show you in the next slide also. It's more detailed. It is there. Yeah. Just let me explain. Then I will go back to the other also. What happened at certain point, as you know, this is a typical case where we have white dwarf, and this is a main sequence companion. So this means this was earlier M1, that is a star of more massive than the main sequence companion. And the larger mass, they have less main sequence lifetime. So it evolved, and through its various phases of evolution, it finally landed to become like a white dwarf star. In such situation, what will happen? This has become compact, and if you see what we call equipotential surface of these two combinations, then this is compact, this is large, but this is still on the main sequence. But its atmosphere has, some of the material of this star, they pass on to the compact object, and that's what we call accretion disk, and it becomes hot star, and there are many, interesting things happen. And in fact, that's why it all depends what type of evolution is going to take place. It depends upon primary and secondary, and with evolution, those things dictate their further evolution. I would just like to just mention, because this is not my topic of discussion today, that if we have white dwarf neutron star combination as a binary, or neutron star as a binary, then we need relativistic astrophysics, whatever Newtonian, things which we are talking about. Here energy and conditions, environment becomes relevant for relativistic and high energy physics. And in fact, pulsars, there are many interesting things happen if you have black hole. Pulsars, they are well known, they are spinning neutron stars. Gravitational wave astronomy, as you know, this is latest latest messenger which has opened. It's not electromagnetic radiation, but it's a very valuable information it provides about astrophysical problem. And in fact, some people say that it has yielded very fast Nobel Prize within few years of its discovery. The people who were responsible, they were awarded with their contribution in the terms of Nobel Prize. Stellar evolution or evolution of binary system depends upon what type of combinations are happening. In high energy zone, in compact objects, the evolutions are quite different, while in other things we can say it's non-relativistic depending upon the physical conditions. Anyway, this I just explained you, and in later my few slides, 5-6 slides, I will be basically talking about these type of binaries where we have stellar collisions during dynamical interaction of binary with single star other binaries. And in this case, mass transfer takes place from this to this, and its evolution is dependent upon that. And these examples, how they behave at different wavelengths, that's what will be the topic which I'm trying to discuss you with one example. And here I'm trying to explain you what is blue stragglers, how they named, and how they were discovered in the beginning, and what mystery they have for us, why we took so long time to understand their progenitors. Still, we have not fully understood them. This is a color magnitude diagram of a globular cluster M3. It is, if you see a large fraction of stars, they follow what we say evolution of a single star. But there were a good fraction of stars which are not following similar evolution, because as per hydrogen burning, if you have a star here, turn of mass here, which is less than 1 solar mass, and this is the isochron for 1.7. So as you can say, a good fraction of stars, they are showing mass similar, much larger than the turn of mass. So BSS, that is blue stellar stars, are located along an extrapolation of main sequence. They are brighter and bluer than turn of mass. Sandage discovered them in 1953. Location suggests that these stars are massive than cluster population, confirmed by few star measurements made recently. And those measurements were made using this binary orbital period and detail study, which I outlined in my slides in the beginnings. But it was very clear that globular clusters have no evidence of star formation. Mass transfer process between binary companions up to complete coalesce and merger of stars introduced by direct collisions. These seems to be the most likely reasons for these things, and there are observational evidence for this. So being more massive than average cluster stars, blue straggler stars in globular clusters, they sink towards cluster center due to dynamical evolution. In fact, this is a cartoon prepared by one of the PhD student in IIA. It conveys everything what I just said. In the beginning, when they were observed in M3, people straight away said that they are not cluster member. Because if you are cluster member, all the cluster members, they were formed together. How you can have your location different than what we principle follow? And people, then they said, look, you are not a member of our family. But ultraviolet observation and latest kinematics, proper motion, all these things indicated that no, they are cluster member. And then immediately the question came, what is the reason for them? And those regions, binary star evolution, in fact, is able to help these location of these stars. And that's what I will try to explain you in my further slides. So this is one of the paper which is accepted for publication in Journal of Astrophysics and Astronomy. And this, whatever few slides I'm showing, they are based on AstroSat U-bit observation. As you know, Space Observatory AstroSat, it has many instruments. So here I'm just using the data taken with this, and this UOC means Ultraviolet Open Cluster Study, and this is the 4th paper, and discovery of diverse hot companion to blue stragglers in a cluster named King 2. Yeah, so this is a HR diagram where location of the, these blue stragglers are shown, and this is white dwarf location is also shown. And this location can be understood mainly on the binary having different type of combination. They could be detached, they could be semi-detached, or they could be contact binaries. And the detailed analysis, multi-wavelength observation and all those things, I'm just quoting the result. They indicate that the blue straggler stars, they have effective temperature 5,750 degree to 8,500 degree. Their radii in terms of solar unit 1.4 to 5.7 times solar radius. Luminosity is 5.6 to 5.7. This is 57, sorry, not 57. 5.6 to 57 times solar luminosity. Mass is 1.2 to 1.9 solar mass. While the hotter component, this is the blue straggler, but they have companion which has a hotter component, and these since it's a low, it has a hotter component has very high temperature, 14,000 to 40,000 degree Kelvin in this range. So the most of the emission from the hotter component, it's not in the optical wavelength, but it comes in the UV, and that's where UV observations becomes very important. And their radius is very, they are very compact object, as I showed you in earlier slide here. This is compact object, and this is the main object. And so main object is, in this case, which is acting like a BSS, it is emitting at optical wavelength. But hotter component, compact object, which has a radius, as you can see, very compact, very much smaller than the size of the sun, they emit UV radiation. So hotter components, their spectral energy distribution indicates that they are in the core helium burning phase. Their binary nature is not well known because we are not able to observe them. Only we are able to observe integrated light because of their large distances. And that's where optical spectroscopic studies with this major telescope, which is 3.6 meter at Devasthal, or similar telescope anywhere in the globe, will help in understanding the nature of these stars. Now I switch over to the variable stars, and here research on variable star is very important. Why? Because it provides information about stellar parameter, very important parameters like mass, radius, luminosity, temperature, internal and external structure, composition, and other things. Some of this information would be difficult or impossible to obtain any other way. It is the nature of variability that provides clues to the answer. These things, while through observation, we can understand them. Variable stars play a crucial role in our understanding of the universe. For example, Cepheid variables, they are considered as a standard, having standard brightness. Hence, they are used to determine distances to faraway galaxy, determine age of the universe. Variable gives us glimpse into the future evolution of our star, like sun, that how it will happen. Accretion disk in cataclysmic variables help us to understand larger scale disk behavior, like the activity inside active galaxies and supermassive black holes. Supernovae have led us to the surprising realization that the expansion of the universe is accelerating. Even the search of extraterrestrial life is illuminated by variable stars. Transiting extrasolar planets provide clues into the process and planetary formation. And the very stuff life, as we know, it is made of cosmos, from hot and stars that explode in the final stages of evolution. So study of variable stars are very important. Here there is a large, you can say zoo of variable stars, which I am just trying to, name few of them, like solar-like stars. Then we have, they follow this type of path, RR Lyrae. And there is a very important phase in most of the stellar evolution, as you see, what we call instability strip. I mean, if you see here, this is main sequence. This is what we call instability strip. What is instability strip? If you recall those stellar structure equations which I displayed earlier, during certain phase of star's life, the star becomes unstable. It means it contracts and expands. And during that intrinsic variability, we have different type of stars, RR Lyrae, Delta Scuti, and Cepheids, and many more like Beta Cepheid and Platinum Nebulae type of, many type of variables we have. And it is the zoo which are studied in this, and they provide valuable information about internal structure of the star. I mean, here I like to say that if you have a coconut, fruit, as you know, when it is filled of water, if you want to know, you shake it. So whatever things come from outside it, that's what we learn. And in fact, in case of sun, Udaipur Solar Observatory, they were involved in a extensive global monitoring program, which was called GONG, Global Oscillation of Solar Star. It participated and they provided very valuable information where TIFR scientists, IIA scientists, and other people have also participated in those, detailed analysis. Now, can I have 5-10 minutes, please? Hello?
Yes.
Yeah, I think I started around...
3 or something like that. And yeah.
Oh, so I have about 10 minutes, okay?
Okay, fine, yeah.
Yeah, then I will finish.
Yes, okay. Sure, go ahead, please.
Thank you. So now I would like to, as Dr. Suman told me in introduction that there is a Devasthan observatory, and I actively participated in establishing it. IIA helped quite a lot, and many other astronomers from not only our country, from globally they helped. So this is the observatory which looks like today. It hosts 3.6 meter Devasthan optical telescope, which is modern thin mirror telescope. It also hosts a 4 meter liquid mirror telescope and 1.3 meter Devasthan fast telescope. So this is 1.3 meter, this is 3.6 meter, and other things. If anybody is interested, I'm just quoting, the reference. This optical telescope at Devasthan Observatory, Nainital, it has appeared in Resonance Journal published by Indian Academy of Sciences in the month of November. So more details can be found there. We have also published an article, about the 3.6 meter dot in Current Science. Gist of this thing, that this facility and location of the site, I will just mention in few words what are the beauty of this. This telescope is able to provide angular resolution up to 0.4 arc second, which is very good number for the ground-based observing facility. It has dark sky And sub-arc second imaging means the atmosphere is good and stable there, that sub-arc second imaging for a large fraction of observed time is possible. Last sentence, actually, before establishing this observatory, we carried out site survey. During site survey, we found that if proper care is taken while we are building the infrastructure, that is, we don't deteriorate, then we can find something. So this indicates very clearly recent observation, because 3.6 meter started operating in 2016. Observation since then, they indicate that the site has not degraded as care was taken in building using materials of low thermal mass. More things, I am not talking, but it means the care and using modern technology. And here I would like to definitely mention Shyam Tandon. I mean, in fact, most of you who are in Ayuga and Pune, they know him. He was, in a sense, guided us very, strictly that follow these things, and that's what yielded these specifications. So thanks to Sam. This briefly tells, duration of the project, it took about 8 years. It costed about 2,000 crore rupees. 10% of this cost was borne by, to be more precise, 2 million euro. It was provided by Belgium. So it's an Indo-Belgium telescope. And, all these structure, what you see, it's a huge. It's more than 300-ton weight. And the largest size was single piece. Before making, you cannot make a huge size telescope and shift it, because roads are narrow and many things. So those things were taken care. To cut the story short, it took about 5-6 months to integrate and assemble. It was advanced mechanical optical system in Belgium which manufactured this telescope, and they were individual parts were carried to the site. They were integrated at altitude of 2,530 meters, and these are some parameters. Now I will just show you two results which have published based on the observation of this telescope. This is one of the cluster, NGC 4147. In fact, Snehalata, she is the first author. They took 339 CCD frames in one filter visual and 302 CCD frames in red filters. And based on that, they studied variable stars. This is a typical light curve which is shown based on the observation taken with 3.6 meter plus other observations that are known for these objects, that is from the archive. And this is the result. They identified 42 periodic variables. Out of them, 28 were discoveries, means they were detected variables for the first time. They host different type of variables, the Jude, which I indicated earlier. They also saw most of the newly discovered stars, and they are located, mostly these 28, they are located in the horizontal branch, red giant branch of the H diagram of this, HR diagram of the cluster. I'm not going into discuss more detail because I'm just telling you the result, and this is the typical light curve which has been obtained with the telescope. This is another, very important observation. It's of the Pluto exploring dwarf planet Pluto enigmatic atmosphere. So this is, in fact, it was jointly, as you can see, there are people from various institutions, PRL, IIA, and other institutions. So what this shows, they observed lunar occultation. And that happened last year in June 2020. As you can see, this star campaign was probing Pluto's enigmatic atmosphere through stellar occultation by the bright star named this it has the magnitude of 12.5. H magnitude, this is in R band, and H magnitude 11.9. And this was observed successfully on June 6, 2020. And this is a beautiful light curve. As you can see, the beauty of the site, it reflects here that, how you are able to get. And these things, people are now using these valuable data. I mean, this is extremely rare event in the sense, as you know, these type of opportunities, they are not very often. They are rarely comes, and once you make use of them, then you use these valuable observational data to understand atmosphere of the Pluto. This slide is showing how good site is. This is essentially, I mean, you can say this diagram. So this is differential magnitude. So in millimagnitude, as you can see, one transit event have been observed by Yogesh Joshi using 130 centimeter. The details are given here, and this site clearly shows that this slide clearly demonstrate that the location Devasthal is very good for optical observation, and in fact observations taken with 3.6 meter near IR where TIFR contributed significantly, they clearly shows that site is as good, I mean very good even in near IR up to 3 micron. It is performance of the 3.6 meter is similar to other telescope located elsewhere in the globe. So this is very, I will say, pleasing, and it's an opportunity for the young generation. And why I showed these 3-4 slides, it's basically because the people who are young and they would like to know what are the opportunity, what are the important facilities which exist. So that's why these 3-4 slides I showed you, and this showed how these things happen, that when they expand and contract, then these variability takes place, and they tells us, light shape of the light curve tells us what is the phase and what are the various features are present in that. So this is the last slide, and it explains you why does star pulsate at all. When a sheet is compressed, it becomes opaque. Photons are trapped inside, heating the gas and increasing its pressure. The high pressure gas expands, becoming transparent. Photons escape, the gas cools, the pressure drops. As the pressure drops, the sheet is compressed by gravity. So it's just like oscillation which takes place, and you see the light curve. And as I told you, they are very variable because they are used as a distance indicator. And this you can see why they are used distance indicator, because the two parameter which you observe, luminosity and period, and they are related like this. If you have type 2 type of variables, then they are related like this. If you have type 1 type of Cepheids, classical Cepheids, then they are related like this. And if you find their type, if you find their period, luminosity, you can determine from period. And once you know the luminosity from now other sources of Gaia data and other things, we can find out their distance. And once we know the distance, other parameters can be, I mean, not even Gaia, here using period luminosity relation, we can find out the distance. So they are very variable, and these were some glimpses of this. Thanks for your patient hearing. And this is the Himalayan peaks. If some of you can visit Devasthal, you will see from there, it's about 120 degree, very clear sky on this. Thank you. I would like to invite questions from the participants.
Thank you, Professor Ram Sagar. Yeah. So I think if you have any questions, either you can unmute your mic and ask it, or write it in the chat box. Hello.
Yeah,
Are
Suman.
there? Yeah. I am just trying to see if there are any
So,
questions.
yeah,
So
this
far, I
is
don't see. So far, I don't see.
actually, I find that this is one of the lacuna in our virtual meetings.
Sorry. In the accreting binary slide, there was something called hotspot. What is
Yeah.
that? And how does it form? And then there is another question. What is Chandrasekhar mass limit?
Okay. So
There are
let
two
me,
questions.
yeah, fine. So I will, yeah, just let me go there and then explain. Yeah. So let me first answer the Chandrasekhar mass limit. You see, when, as you know, in the stellar evolution, yeah, here, take for example 5 solar mass suns, a main sequence star. It goes through various phases of stellar evolution. When in this process there is a large fraction of the mass or significant fraction, it depends upon what physical processes are taken, they are thrown away from that, and it is that mass, as you can see, this is that mass which is being thrown here. This is a compact object, and in this case this accretion disk which is here and this matter, when they interacts, then the physical conditions, this hot spot could be region, for example, if you have a cataclysmic variable, there could be those physical processes which are emitting X-ray. They may exist there. So it depends upon what type of material, what is the physical conditions, what temperature and other things which are there, and how it is interacting with the accretion disk. That's how the property of the hot spot will be determined. And it depends upon neutron star. I mean, like cataclysmic variable, you have different type of things. Like in astroset, people observe a lot, and you might be seeing at different wavelength they behave different. In this process, the mass, you see, in all these process, you remember I was telling that radiation pressure and gravity, they are balanced. That's when they are balanced, we say star is stable. Gravity, suppose the mass becomes, let us say, 1.2 solar mass, then we have some gravitational pull inside, and that pull need to be balanced by the internal pressure. That internal pressure, as long as nuclear reaction was going on in the core, it was the radiation pressure which was balancing it, which I showed you in those earlier equations. But when there is no source of nuclear reaction, for example, compact object, if you take neutron star or white dwarf, then we don't have nuclear reaction taking place in their core. Then what is the thing which is stable? Because at that high temperature and pressure, then the entire thing becomes in the terms of electron, and electron degeneracy pressure becomes responsible. And why electron degeneracy pressure takes place, as you know from the quantum mechanics, if you try to, two electrons cannot have the same state, this, Pauli exclusion principle. So once electron degeneracy pressure is able to balance, and this balance between gravity and this electron degeneracy pressure happens at 1.4 solar mass, which Chandrasekhar was the first to derive what we call Chandrasekhar mass limit, and that is 1.4 solar mass limit. Was it enough for the answer?
Yeah, there is one more question.
Yeah.
Is the reason for variability for Cepheid variables that you have mentioned is same for
Right.
all variable stars?
No. similar phenomena is there. I mean, for example, yes, yeah. For example, if you see, we have delta scuti, some are very small amplitudes, some are, while I'm saying variable means there will be two parameter. One will be time period, what we called also phase, time period, and other will be amplitude. So the amplitude and time period, they are different for different type of variables, and their shape is also different, and it depends. For example, if you see here the type of mass which are there, for example, if you see along the instability strip, some are giant, some are massive stars, low mass stars. So the basic reason is same, but if you go into detail, for example, here you see rapidly oscillating AP stars. So their physics is different because in the star you have magnetic field also. So if you have rotation, you have magnetic field, all those things play into role. So whatever I was showing here in case of Cepheids, it's a very simplified picture, whatever I said. But if you have magnetic field, if you have rotation coupled with this, then those forces will also play a role, and they, are different for different things, broadly speaking.
Okay, so I guess if you have any further questions, you can email to Professor Ram Sagar, right? Professor Sagar, that would be fine.
Yeah, it will be fine. And yes. I think you have my email address, please.
Yes, and if you could share your slides with Obhirup probably, and he will circulate it among the participants.
I will just now send both of, Obhirup. Yes, I will just.
Yes. So that if they have any further question on those topics, they will basically mark that and send you back and ask you back. Yeah.
No, thank you, Suman. Thank you.
Thank you very much. So yeah, so probably Professor Sagar, if you could stop sharing the screen. I think Professor Ram Prakash is already here. I would request him to share the screen. Hello, Professor Ram Prakash, can you hear me?
I can hear you very well, Abhirup.
Yeah, I'm Shuman, actually. So if you could please share your screen, the slides, and we can. Actually, there was a mishap with Nishim Kanekar's talk. He couldn't actually give the talk in the end, and we spent half an hour. That's why Professor Ram Sagar came in his place. That's why schedule is a little messed up. I'm sorry for that.
No problem. Yeah. Yes, Abhirup, talk to me. Yes.
Yeah. If you could share your slides in the screen, so there is a share button at the bottom. You will find, and then.
Started sharing.
Yeah. I think it is coming up. Yes. Now I can see your slides. Thank you.
I'll make it full screen.
Yes, please. Yeah. If you could also, if it is possible, to switch on your video input, then students can probably see you as well.
Does that look good?
Yeah. You are visible now. Thank you very much. So I will just introduce you quickly.
Yes, I do hear a little bit of echo.
Okay, so
maybe others who are not speaking could mute.
Yeah, so okay, I will try to. No, I cannot mute them manually. So yes, it's a request to all. If you are not speaking, please mute your microphone. That would be nice.
Thank you. Now it is much better. Yes, thank you. Abhirup, can you hear me?
Oh, sorry. I kept myself mute. I'm sorry.
Yeah, no problem.
Yeah. So Professor A.N. Ramprakash is with us. He is associated with Inter-University Center for Astronomy and Astrophysics, Pune, and he has basically done his PhD in optical instrumentation and the main focus was IMPOL and imaging polarimeter at IUCAA itself. And after that, he has done a postdoc in University of Cambridge in the Institute of Astronomy. So his main research interest is largely and setting up the IUCAA Girewali Observatory, and he also worked on CCD and near-infrared detectors and data acquisition systems, cold optics, cryogenic design, testing and assembling integral field units using optical fibers, OH suppression spectroscopy, polarimetry, etc. And in terms of science, these are mostly instrumentation related research, and then in terms of science, he was involved in working with pre-main sequence stars, brown dwarfs, galactic molecular clouds, and observation of transient phenomena like GRBs, blazars, and supernovae. So, Professor Ramprakash, the floor is yours. You can start. Thank you.
Thank you. Good afternoon, everybody. I hope you all can hear me and see my slides. The topic which was given to me was astronomical instrumentation, which is really a very, very broad title. So I have taken some liberty because the time is limited and I cannot obviously cover every aspect of astronomical instrumentation in such a short talk. So I will try to focus on certain areas, especially if you look at the electromagnetic spectrum here, it ranges all the way from radio at this end to through infrared, visible, ultraviolet, and then all the way to X-rays and gamma rays at very short wavelengths. So my main focus today would be in this regime, which is kind of near infrared, visible, near ultraviolet kind of wavelengths. That's what I would mostly focus on. And for ground-based astronomy, I will not spend much time on space-based astronomy. But towards the end, I will try to give a glimpse of the challenges in radio astronomy instrumentation, etc., and what is the future? Where are we going towards over the next 10 years, 12 years? Where will these facilities go towards in terms of technology and capabilities? So that's what my focus would be. I will not be covering anything about high energy facilities or instrumentation. I will not talk too much about radio astronomy and instrumentation, except to mention them in passing. Now, having given that preamble, let me start with a basic question. If you talk to an astronomer, the basic tool of an astronomer is a telescope. So you start with the question of what does a telescope do for an astronomer? That's the main question. Why do astronomers need to use telescopes? I try to break that question down into initially simple terms, and then maybe try to quantify things a little bit more as you move on with the later slides. So if you ask that question, and the answer is in simple English, it says, if you look through a telescope, objects appear closer. That's what you would typically answer. And bringing an object closer has two aspects. One is you start collecting more light from that object, and you will be able to see more details on that object. So these are the key two capabilities which a telescope do. If you look at a celestial object with your eye, you collect a certain light through your eye, you will be able to discern a certain level of detail. But if you look through a telescope, those two capabilities are improved. The amount of light you collect and the amount of detail you can see. Now, there are two factors of the telescope, two parameters of the telescope that define these two capabilities: how much brighter an object becomes and how finer details you are able to see. And those are these two. The diameter of the telescope is what defines how much more brighter an object becomes. The bigger the diameter, you collect more light, and the object appears brighter to you. And it's the focal length of the telescope which defines how much more details you are able to see. The longer the focal length, the telescope will be able to is capable of seeing finer and finer details. If you compare numbers, the first telescope which was used, at least as far as we know, which was used about 400 years ago by Galileo Galilei for astronomical applications. Telescope did exist before that also, but Galileo was the first one to use it to look at the skies and record those observations and infer about the celestial objects and phenomena. So Galileo's telescope had a diameter of about less than 2 inches. The largest optical telescope which exists today, the Keck telescope in Hawaii, has a diameter of 10 meters. So it's a huge jump. Similarly, Galileo's telescope had a focal length of less than half a meter, but the largest telescope, Keck telescope, can have a focal length of 150 meters. So you can see that in both these capabilities, both in diameter as well as focal length, both in the ability to collect more light and in the ability to see more details, our technology has come a lot over the last few hundred years. We have progressed substantially in both these abilities. Now, having said that, one could ask, okay, if the telescopes bring objects closer, how far are these objects which you are trying to make up here closer? They are, these are enormous distances. We all know that when we talk about celestial phenomena, we are talking about very, very large distances. But let us try to put some comparative scale in our mind to understand what we are talking about. The shortest astronomical distance you can typically talk about, and which is very relevant, is the radius of the orbit of the Earth around Sun. As the Earth goes around the Sun, it describes an orbital thing and an average radius. It's an elliptical orbit, but an average radius. And to calculate that, we can use information that the light takes about 8 minutes to travel from Sun to Earth. And 8 minutes converted to seconds times velocity of light, it turns out to be about 1.5 into 10 to the 11 meters. That is what one astronomical unit is. It's a mean Earth-Sun radius. But this itself is not a sufficiently large enough unit for astronomers. So astronomers use light year as an equivalent unit to measure distances in space. And the light year is the distance traveled by light in 1 year. All of us know that. So there are about pi times 10 to the 7 minutes, pi times 10 to the 7 seconds in a year times the velocity of light. So it's about 10 to the 16 meters is a light year. Even this is not a sufficiently large unit for measuring distances to celestial objects. So astronomers use a related but slightly different units very often. Let me try to explain what that unit is. If I take a stick like this and draw 2 lines from the edges of the stick so that they converge at a point, and then if I move the stick farther away, the same stick, I keep it farther away, this angle at which these 2 rays converge at your eye, if you are sitting here and looking at this stick, the angle between these 2 rays keep reducing as you keep moving the stick away. Now, if I take a stick which is 1 astronomical unit in size, this size, 1.5 into 10 to the 11 meters in size, and ask the question of how far do I have to go so that the angle subtended between these 2 rays is just 1 arc second. An arc second is a very tiny angle. 1 degree divided by 60 is 1 arc minute. 1 arc minute divided by 60 again is 1 arc second. So you can imagine that it's a very tiny angle. So if a stick which is this enormous in size, 10 to the 11 meters, have to subtend only 1 arc second in your eye, you have to go very, very far. The distance is enormous. That distance is called 1 parsec. So astronomers use a parsec also as a typical measuring unit for distances to celestial objects. I explained this here. So 1 parsec you can show is roughly 2 into 10 to the 5, that is number of arc seconds in 1 radian, times this size. So this is r theta. It's just r theta. So you will see that it's about 3/4 times 10 to the 16, 3/4 times a light year. 3¼ light years is 1 parsec. If I take these units and use parsec as my unit and say how far is the nearest star to our sun, our solar system, the star called Proxima Centauri, it's about 4.2 light years away or about 1.3 parsecs away. So this is very typical in interstellar distances. If you take our galaxy and see how far away are stars, typical interstellar separations or distances are of the order of a few parsecs here and there, or so a few light years in equal units. So that's the distance between typical stars. Now, if I ask what is the size of our Milky Way, it is 20,000 times that of interstellar distances. So if interstellar distances are about 1 parsec, the size of our galaxy, the Milky Way galaxy, is 20,000 parsecs or 20 kiloparsecs. Now, if we try looking at what are the distances to other galaxies, the closest galaxy to our galaxies are the Magellanic Clouds. They are about 50, 60 kiloparsecs away. The nearest large galaxy to our galaxy is the Andromeda galaxy. It's almost a megaparsec away, which is another factor of 1,000. And if you ask what is the size of the visible universe today, that's again another factor of 1,000. It's 4,000 megaparsecs or 4 gigaparsecs. So you can see that from interstellar distances, which is of the order of parsecs, which is itself an enormous distance. Size of the galaxy is about in kiloparsecs. Intergalactic distances are megaparsecs, and the size of the universe itself is in, you can say, a few gigaparsecs, visible universe. Now you can see that these are all enormous distances. So what does it really mean when you say a telescope brings objects closer? So the only way to understand that is by the two properties which I mentioned earlier. One is that the telescope makes an object brighter, appear brighter, it collects more light from that object, and it allows you to see finer details. Those are the ways in which the object appears to us to be closer. And other than that, these distances are all infinite compared to any scale we can think of on Earth. And those infinite distances, there's no meaning in saying that telescope brings objects closer at those infinite distances. So those are the two aspects. Now let us ask this question. I am sitting somewhere on Earth and looking at a star in the sky, which is a point source. It's just a point, a dot in the sky. Now, how does a telescope, which is pointing at the sky, collect more light just because the diameter is larger? Because it's just a point source. How does it matter how big the telescope is? So let me try to explain that a little bit here. So if I think of this star, light is radiating away from that star in all directions. So light is diverging out of that point source in the sky in all directions. So as time passes, this light would have traveled further and further away. And over a long period of time, it would have traveled these enormous distances and reached where we are sitting on Earth and looking through the telescope at that star. Now, what you see happening is this curvature of the wavefront, which is reaching us from the star, although the wavefront looks spherical as it emerges from the star and diverges away, by the time it has traveled these enormous distances, the curvature has become almost negligible. This is a circle of infinite radius, which means basically it's a plane. Which means that the rays which started off diverging from the star appears to be parallel to us when we look through a telescope. So that's a key point. These distances are so enormous that although the rays start diverging out of the star, by the time they travel this enormous distance and reach us, they appear parallel to each other. The angle between them has become very, very tiny and almost immeasurable. Now, the advantage of this is, if I have a telescope here and it's collecting light from this much part of that wavefront, this will make that object this brighter. But if I make that object, if the telescope was larger, it will collect light from a larger area of that wavefront, and therefore the object will appear brighter. So it's just a question of how much light from that star my telescope is able to collect out of that wavefront, and that much brighter the object becomes. That's how a telescope makes an object brighter. Now let us look at the other aspect. How does the telescope allow an object to be, to see finer details of an object? Now, there's no point trying to see finer details of a star. The star is too tiny and too far away that you can't discern the features on the star. But if there is an object like a galaxy or a nebula in the sky, you should be able to see details on them. And in order to understand that, you just put a second star right next to the first star. So the light from this star, the red one, also would be diverging away, just like the one from here. But by the time they reach where we are sitting on Earth, the wavefront which is arriving us will be actually centered on this red star, while the black one is centered on this black star. So the rays are, while they are parallel to each other from each of the stars, between the stars there is an angle of arrival, because this plane is centered on this star, the black plane is centered on this star. So they arrive at a tiny different angle. So if the telescope is able to distinguish this angle of arrival, it will see these two stars as two stars, or 2 points on that object. If the telescope is not able to see this separation between these angles of arrival of these rays, then to us, looking through the telescope, this will appear like one blob of light. We are not able to distinguish the differentiation of the angle of arrival from the two objects, and then it will appear like one blob of light. So that is the trick. The diameter defines how bright an object becomes. The focal length of the telescope is what defines whether it is able to distinguish this angle of arrival or not. Let me try to understand this a little bit more with this illustration here, and put that in a quantitative fashion. I am representing a telescope with a lens here. So any optics can be reduced to an equivalent lens with a focal length and a diameter. So this lens represents our telescope, and it's pointing to a star in this direction, along this direction. So the rays from the stars are arriving, and this lens would converge that into its focal plane, because these rays are parallel to the optic axis of the lens. They will converge at the focal plane. Now, the diameter of the telescope is what defines how much light it collects from that star. That's clear from last slide. If I have another star, the red star, which is slightly off axis from the black star, the light from that star, as we discussed in the previous slide, arrive at the lens at a slightly different angle compared to the black lens. So of course, those red lines will go and converge at a different point at the focal plane of the telescope. And then you get two images. This is the image of the black star, this is the image of the red star. Now, as you can see, if this angle is theta, this is the angular separation between the two stars in the sky, that is theta. And this distance is focal length of the telescope. You can see that f theta is h for small angles. So f times theta is h. So that means f theta is h. If I write theta is equal to h by f radian. So for a given separation of the two images and the telescope focal length of f, the corresponding angular separation of the object in the sky is given by h by f radians. Now you can ask, what is the angular separation what is the linear separation you are going to get for given angular separation in the sky? That is called the plate scale of the telescope, which is nothing but this expression expressed in terms of arc seconds instead of radians. So there are 206,265 arc seconds in 1 radian divided by f if expressed in millimeters. It will tell us that the plate scale P is 206,265 by f. That is the number of arc seconds in angular separation of a star in the sky for every millimeter linear separation at the focal plane of the telescope. So what it means that it just depends on the focal length, the separation. So that is how, if two objects are separated by a given angular separation in the sky, we can define whether they will be sufficiently separated at the focal plane of the telescope so as to be able to see them as separate objects, or will they become one blob of light and we don't see them separately. And that depends exclusively on the focal length of the telescope. Now, having explained to you how the telescope allows you to see fainter objects and in finer details, let us try to quantify this a little bit more. This has been mostly qualitative, but let's try to make it more and more quantitative. Now, the question here is, yes, the telescope makes objects brighter. Now, how faint? What is the faintest object we can see in the sky? Can we see objects fainter than the sky itself? So if you go out today in the daytime and look at the sky has a certain brightness, and you don't see stars because the sky is brighter than the stars. But on the other hand, if you go out in the night and look at the sky, the night sky also has a certain brightness, but many stars are brighter than that, and you will be able to see those brighter stars. So is the faintness limit of how faint an object you can see set by the sky? Is it the faintest object you can see has to be brighter than the sky, or can we see objects which are fainter than the sky? Now here is an illustration. This is a patch of the sky. I'm putting a star there, a pretty bright star, so you are able to see it. Now I'm going to make the sky brighter, or the star fainter. I made the star fainter than before, so it becomes dimmer and dimmer, and then dimmer again. It's so dim that I cannot see the star across in comparison to the background sky. But I just will make the sky a little fainter now so that the star appears. See, when I made the sky darker, the star is still there. You're unable to see that only because the sky is brighter. Now, is this the limit? You cannot see anything fainter than the sky. Now, if you ask that question, I will answer, look, I will measure the total light coming from this direction. I will measure the total light coming from this direction. Of course, if I subtract this from this, you will see some excess light from this direction, and then you can say that the star is there. So just subtract the sky off. You look at the total light from this direction, some 100 photons plus 1 photon, 101 photon, 100 photons from the sky, 1 photon from the star. Yes, you can see that. But you get 100 photons from this side. So subtract and 1 photon extra because you have a star. So just subtract off. Is that a problem? Then you can see any faint object. It doesn't matter how faint it is. You can keep subtracting the sky off and keep measuring. Now the problem is, whenever you make a measurement, like the total light coming from the star in the sky here, or the total light from the sky alone in this direction, any measurement is aligned, or it has an inherent uncertainty in measurement. And it so happens that when you're counting photons, if you collect n photons from any object, there is an inherent error of sigma n, which is equal to root n. So any measurement of a photon, of a brightness of an object, by collecting n photons from it, you only know the brightness of an object with an accuracy of n plus or minus root n. This is not because of any technology limitation. It is not because your telescope or your instrument or your detector is non-ideal, etc. This is inherent in the nature of photons and counting photons. This is called photon noise. It's a way. This is a physical phenomena. It's nothing to do with. It's a fundamental phenomena. If you collect n photons from an object, next time you collect n photons, you will get. Next time you collect photons from that object, you will get a slightly different number. Next time you collect it, you get a slightly different number. You take the average of all that number with a large number of experiments, you get n photons. But the standard deviation of the multiple measurements will end up being root n. That's the way it works. That's the way photons work. Now you cannot beat that. So if I point my telescope here and measure 101 photons and point my telescope here and measure 100 photons, each of those measurements are uncertain to root n, which means root of 100 roughly, which means 10 electrons. So I can only say that this sky I measured with 100 photons I got in my exposure, but I know that value only from 100 plus or minus 10. That clearly says that you cannot say for sure whether there is an excess of 1 photon in this direction, because your measurement uncertainty of this part is already 100 plus or minus 10. So how well you measure the sky is going to define how faint you can see. And that's what I'm going to illustrate in this table. So I have 5 columns here. First column tells us what the light I'm going to collect from a star. The light I'm going to collect from the sky is in this column. Root of this is in this column. Root of this is in this column. And I will say that we will define a quantity called signal to noise ratio, which is nothing but the signal, which is the number of photons I collect from the star, divided by noise, which is these two terms of uncertainties added in quadrature. Let's not worry why they added in quadrature right now, but let's take that the total noise effectively is the quadrature sum of these two noise sources. One noise when counting the star photons, the other noise is counting the sky photons. That is where the noise comes from. So let us look at some numbers. I look at a very faint star which is only producing 1 photon in my exposure, but the sky around it is 100 times brighter. So it is producing 100 photons during the same time. So the error in measuring 1 is 1, but error in measuring 100 is 10. So if I plug these numbers in this expression, this 100 dominates. So you can ignore sigma squared star here. So the signal to noise ratio ends up being 1 over time. This is about 1 is the number of photons you collect from the star, and sigma, this whole thing is roughly 10. So 1 over 10 is your signal to noise ratio. Your star light is 10 times fainter than your noise in measurement. So you don't know whether there is a star or not. Now you don't give up. You say, okay, I still want to make a measurement and see if there is a star out there. I make a bigger telescope, which collects 100 times more light. So from the star, it's going to collect 100 times more light. Of course, from the sky also, it collects 100 times more light. Now, if I calculate the signal to noise ratio, the signal is 100 now, the numerator. The denominator is also 100 now, because you ignore this 10 related to the 100. So your denominator is also 100. So the signal to noise ratio is 100 over 100, which is 1 now. Now I'm saying, hey, my signal is at least comparable to the noise. In this case, it was 10 times weaker than the noise. Now it's comparable to the noise. Okay, that's a good sign. Let us make a telescope which is even bigger, 100 times bigger. I collect more light, 100 times more light from the star, 100 times more light from the sky, calculate the signal to noise ratio. Now the uncertainty in measuring this, the sky is 1000, because 1 million photons if we collect, uncertainty is root of 1 million, which is 1000. And this is your signal, which is 10,000. So 10,000 over 1000 is your signal to noise ratio. Now the signal, which is the light from the star, is 10 times more than the uncertainty in your measurement. And therefore, you can confidently say that, look, there is a star there. I measure it with a signal to noise ratio of 10. So that is why astronomers make bigger and bigger telescopes. They want to see fainter and fainter objects with the higher and higher measurement accuracies, better and better signal to noise ratios. They make bigger and bigger telescopes to collect more and more light or more and more photons in shorter and shorter times. And therefore, your measurements become better and you are able to see fainter and fainter objects. So the summary is, yes, the sky sets a limit of how well you can measure. But if you are resourceful enough, you can put in the effort to make a sufficiently large telescope to collect sufficient number of photons. You can beat the sky. The sky while tries to set a limit, astronomers find a way to beat the sky. Sky is not the limit for them. That's the final message. Now, that is why astronomers make these bigger and bigger telescopes. You can see this is the top of a very tall mountain called Mauna Kea in Hawaii. It's about 4,200 meters above sea level. You can see very large telescope there. These are the twin Keck telescopes, which I mentioned earlier, 10 meters in diameter. This is the Subaru telescope, the Gemini telescope, and all that. They are all very large telescopes, 10 meters, 8 meters in size, and so on and so forth. So this is just a zoom-up view of the Keck telescope. There are two of them on the same mountain. You can see the dome, and you can see the primary mirror of the telescope, two of them. And to set the scale, this height here is almost 2 floors high. Okay, or you can see trucks parked there. So this is an enormously large building set up or facility that has been set up on top of a mountain, which is 4,200 meters in height, almost half the height of Mount Everest. So astronomers or human beings do take enormous effort to set up these facilities to look at the sky and study the sky. Now, this is another example in Chile, the very large telescope. The Europeans have built 4 8 meters diameter telescopes. The primary mirror of each of these telescopes in 8 meter in diameter, and there are 4 of them on top of a mountain in Chilean Andes. And you can see that the mountain is so high that the clouds are all below the mountain. The mountain is above the clouds very often or most of the time, so that you can look at the sky without the hindrance of the clouds. Now going forward, the world is now, there are several groups around the world who are building even larger telescopes. And the first of them is called the giant Magellan telescope, which has a 25-meter diameter almost. You can see it's not made of a single piece of glass. Each of these mirrors is 8 meters in diameter. Okay, so there are 7 of them arranged in this fashion to form a telescope of almost 25 meters in diameter, made of pieces of glass, multiple pieces of glass. This is a 30-meter telescope. In here, instead of circular pieces of glass, they are using hexagonally cut glass pieces put together into an array of 30 meters in diameter. And there are about 500 of such segments which form the 30-meter diameter primary mirror of the telescope. And the third one is the European extremely large telescope, an even bigger telescope of 39 meters. And you can see this is also made of hexagonal segments. You can see the edges here, but the hexagonal segments are again 1 meter, 1.5 meter in size, edge to edge. But this whole diameter is 39 meters, and so it's an enormous telescope. You can't see the individual hexagons in this figure, at least. So these are huge facilities which are coming up. Astronomers are pushing the frontiers now to build these facilities to look at the sky and detect fainter and fainter objects. In this endeavor, astronomers have to struggle with a lot of natural and technical limitations. And one of them is the fact that the sky is not a static object, it is moving. So you can see here, it's a long exposure image. This point is the pole, north celestial pole. And you can see if you take a long exposure taken to pointing the camera toward the north celestial pole, all the stars draw their movement, trace a trajectory which looks circular and centered around the North Pole. And that is obvious why it's happened that, because it's not the stars which are really moving. We are sitting on Earth and rotating around Earth's axis. So if we extend the Earth's axis and find where it hits the sky, that's the North Celestial Pole. So sitting on the Earth and going around, it will appear as if the sky is going around that point where the axis of the Earth hit the celestial sphere. So these circular trajectories are just the trajectories of stars as they appear to us while looking at them sitting on the Earth. And the rate at which they move is clear. In 24 hours, the Earth rotates 360 degrees. So every second, the sky seems to be moving 15 arc seconds. Or every hour, the sky seems to be moving 15 degrees sitting on the Earth. And this is just a time-lapse movie showing the same thing. The North Pole is somewhere here, and you can see the star trails describing concentric circles. Now, in order to track the movement of these objects in the sky, you cannot build a static telescope. This telescope also has to move along with the motion of the Earth or apparent motion of the stars in the sky and keep collecting light, because ultimately the number of photons you collect, the total number of photons you collect, is what is going to define how accurately you can measure the light from the star, as I explained earlier. If you collect n photons, root n is the uncertainty. So you need a big telescope, which is also going to stare at the same star and take a long exposure, star, galaxy, whatever, and take a very long exposure so you can collect adequate number of photons, first of all, to beat the sky, and also get enough signal to noise ratio in your measurement. So the telescopes have to move around in multiple axes. You can see one axis is this movement, the other axis is the base movement. This is just an animation of the 8-meter Gemini telescope, one in Hawaii and one in Chile. And you can see that telescope has to move in multiple axis system. So it's not just a very static laboratory system which is going to look at the sky and measure. It's out there in the open on top of these very high mountains and collecting light for a long time. And it has to keep tracking objects in the sky. While tracking objects in the sky, the sidereal rate is the rate at which the stars appear to move to you. As you can see, when this telescope tube bends around, moves around while tracking, all kinds of disturbances happen which misaligns the telescope's optics, like the gravity. The gravity is changing. Whether the telescope is pointing like this or whether the telescope is pointing like this, the effect of gravity is changing and the optics can get misaligned. The large structure, the temperature can change, there's wind blowing, very high wind blowing and disturbing the pointing of the telescope, all kinds of disturbances, and the telescope has to work in spite of all this natural and technical limitations. But I will not spend too much time describing those things, but I will spend some time explaining to you what are the fundamental limitations in optical astronomy, and that is what is called the seeing. I'll explain to you in a minute what seeing means. That is why the title of my talk was called Seeing the Stars. So let me try to explain what seeing is. Now, before explaining that, let us just refresh our minds in our understanding. When light travels from a distant object like a star or a distant galaxy, it is traveling through this enormous empty, almost empty space while it's traveling to us. But by the time it reaches the Earth's atmosphere is a very dense medium compared to whatever is out there in free space, open space, interstellar medium, intergalactic medium, etc. There is very little material there. But by the time it reaches the Earth's atmosphere of the Earth is a very dynamic and relatively dense medium compared to the interstellar space. Now, this medium is always disturbed by various factors like the solar heating, winds blowing, human activities, or Earth heating, ground radiation. All kinds of things are affecting the atmosphere and making it turbulent. The atmosphere is not a homogeneous medium. It is a turbulent medium. It's always continuously changing. Now, when light passes through such a medium, what happens is the following. To understand that, let us take this kind of graphical illustration where you say, okay, the energy is being injected into the atmosphere at very large scales, called outer scale. The sun illuminating a large area of the atmosphere, ground radiation heating up some part, wind blowing, etc. These are all large scale. Moves atmosphere in bulk, in large quantity density or large volume. There's bulk movement of atmosphere. But within that bulk movement, atmosphere is constantly breaking down. It is constantly breaking down into smaller and smaller parcels of air, smaller eddies. And this continues until a scale called inner scale, where viscosity, etc., stops them from further breaking down. So if you look at the atmosphere, it has scales at all this range, right from the outer scale at which the energy is injected and causes bulk movement of the atmosphere, all the way till the inner scale where it fades and then move out randomly. The atmosphere has all these scales. Now, when light passes through such an atmosphere, happens. So here, and the air here is the air flow over a very long, quiet ocean for thousands of miles. So that's atmosphere. Mountain, and of course, now if I sight a mountain, atmosphere, large undisturbed, the airflow is very smooth here. On the other hand, if the light has passed through this side of the mountain where the atmosphere is very turbulent, non-homogeneous, it will distort the wavefronts. You remember in one of the first slides, I said the wavefront which is arriving on Earth will be a plane wavefront where the rays are emanating parallel. They're not diverging, they're parallel. But those rays will no longer be parallel because each ray passing through these different parts of the atmosphere will be bent in different ways, and that lead to the blurring of the image. So if you are observing Jupiter, for example, from this side of our observatory, you might get a very clear, fine view of that Jupiter, but on the observatory happens to be on this side, where the atmosphere is very turbulent, your view becomes very blurred. You are no more able to see the details. So this is a very serious limitation. The very fact that you are making big telescopes is to see details. But stop the wavefront and it your image produces so fine details. Astronomers on this more quantitative way. Take a laser beam and shine it through a aperture. All the air also you can think of the telescope as this aperture where the image is ideal and the atmosphere is not distorting the wavefront, the wavefront falling here, and the telescope is a plane wavefront. A point to look like telescopes for things around it. Another star, so this laser is another different other than how fast these not one star, and that is defined by what is called the Rayleigh criteria. And what it means is if two stars are separated by angular separation of lambda over d, you are observing a sky at a wavelength lambda, looking at the star at a wavelength lambda, with a telescope of diameter d, the minimum separation in the sky, which you can resolve as two separate stars, is given by roughly lambda over d. So if you have a 10-meter telescope observing at a wavelength of lambda at half micron, this Rayleigh limit is about 0.01 arc seconds. So theoretically, if you have a 10-meter telescope and you are looking at a star, a pair of stars at a wavelength of half micron, if the stars are separated by even 0.01 arc second in the sky, a very tiny angle, 1 arc second is already a tiny angle, and this is 1/100th of that. Even that angular separation, this telescope should be able to theoretically see. Now let us see what happens in reality. So here is another airy disk pattern. I have put, for scale purpose, I have put marked here 0.01 arc second. That is about this size. Now, because of the atmospheric turbulence and the disturbance which the atmosphere introduces into the light beam as it passes through the atmosphere, what will happen is the light of that star, which should have concentrated mostly in this 0.01 arc second area at the image plane of the telescope, will spread out over an area which is half arc second. Half arc second may appear to you small, but compared to what the telescope should have achieved, which is 1/100th of an arc second, half arc second is huge. So this half arc second is so large that area that light spreads out that I can't just fit it on the screen. This is only 0.1 arc second. The light will spread over an area which is 5 times this size compared to this tight, tiny spot it should have been focused on. This is the problem with the atmosphere. Atmosphere is a very, very serious limitation because ideally that light from that star should have focused almost entirely in the size of this circle. But it's actually going to be spread out by the atmosphere over a circle which is 5 times this size. Of course, that's a huge limitation in how fine details you can see in the sky. It's a very, very serious, severe limitation. And this is something which astronomers cannot accept or live with, because it defeats the purpose of making bigger and bigger telescopes. The atmosphere defines how faint an object, how fine a detail you can see. How do astronomers solve this problem? This is what is explained here in adaptive optics. I will quickly run through it. I know I'm probably close to the end of my time. So let me quickly run through this, and then I'll skip a few slides and then go toward the end. So if you think of this box as what is representing your telescope, this is the galaxy or the star you want to observe. Now, the light from that galaxy or star, which are indicated by these blue lines, are falling on the telescope. You find a reference object, a bright star, right next to that galaxy. So the light from that reference object is falling here. And the telescope obviously tries to focus that beam, but before focusing on that, I'll put some additional contraptions here, which are called adaptive optics. Okay, so let me explain what adaptive optics is. What is happening here is this light, before it goes to my final image plane, is reflected off what is called a phase corrector. I will explain what a phase corrector is in a minute. It passes through this beam splitter, where what the beam splitter does is it separates the light from the science object of your target of interest and the reference star. So the reference star light is reflected. The light from the target object is allowed to pass through straight. Now, with the reference star object, you use a wavefront sensor and measure how the wavefront is deviating from a plane wavefront. Imagine there is no atmosphere here. Everything is ideal. The rays should be running parallel like this. But because of the atmosphere, the rays will not run parallel like this. They will come at different angles, and that is what is leading to the image quality degradation. So that deviation of the angles will be measured by this wavefront sensor, provided through a control system, so that the shape of this surface is changed instantaneously every instant, in order to compensate for that deformation of the wavefront, so that the reflected light ends up being a parallel wavefront. So what it does essentially is this wavefront sensor measures the distortion introduced by the atmospheric turbulence, changes the shape of a reflecting surface in a way that that distortion introduced in the wavefront is exactly compensated, so that you get a plane wavefront back, and therefore the diffraction limited image here. Let me try to explain how this wavefront sensing works. If I try to divide this beam of light into multiple lenses, at each point, because the wavefront is distorted, there's a slope in the wavefront, which means if the wavefront was plane, the images formed by this lenselet, this lenselet, this lenselet, etc., will be a clear, an array which is regular in pattern, a regular array of spots. But because the wavefront falling on it has different slopes for each of these lenslets, these spots would move. So by measuring the spot movement, you can see what is the local slope of the wavefront. And from that, integrating it, you know what is the overall shape of the wavefront. That is how the wavefront sensor measures the shape of the wavefront. And then to correct the wavefront shape, you distort this shape. So for example, if the wavefront is distorted like this, and the reflecting surface here is distorted exactly compensating shape. This part is advanced in the wavefront, so this part moves back. This part is behind the wavefront or behind in time. So this part of the reflecting surface is advanced forward. So when the light reflects off, they will come off as plane wavefront. So that is how the correction system works. So a combination of wavefront sensing and phase correction, you create the wavefront which is plane, as if the atmosphere effect is not there or is exactly compensated, and you recover the diffraction limited images. So I will skip some of these slides now because of time limitation. Let me try to illustrate here an example of how an adaptive optics system works. For example, here, without an adaptive optics system, if you look towards the galactic center with a large telescope, you will see all the stars blurred. But once you turn the adaptive optics system on, you can see all that light actually collapsing, and you are beginning to see really fine details of your target. Here is an image of Jupiter without adaptive optics and with adaptive optics. You can see the fine details, which would have all blurred without adaptive optics here. So you can see how much improvement it gives. And here is the surface of moon with adaptive optics. And the other big thing is, here is a star which has been blocked off by what is called a coronagraph. It's not our sun, it's an extra, it's a star somewhere else. And you can see these planets moving around the star. So if the adaptive optics was not there, the light of the star would have filled this entire frame and even more. Because of adaptive optics, you are able to collapse the light of the star into a very, very tiny region, diffraction limited region, so that you can see the presence of planets moving around the star. You can see 4 planets moving around the star in this image. So this is what adaptive optics allow you to do. Now, if you can't do adaptive optics and you can't deal with atmospheric effect, you have to go to space. And that is what is Hubble Space Telescope did. And that is what the James Webb Space Telescope is going to do, which James Webb Space Telescope is a 6-meter diameter telescope, which is going to be launched later this year. And once it is launched, it will sit in space and start observing them. Okay, but because it's above the atmosphere, you don't have the limitations of needing an adaptive optics system. Now let me come towards the end of my talk. If you want to increase your angular resolution even further, I told you if you have a telescope of diameter d and you're observing the sky with a wavelength of lambda, the finest angular resolution you can get is lambda over d. But you can also do a different trick where you take two telescopes which are separated by a very large distance. Here the d is not the diameter of the telescope, but it's actually the distance between the telescopes. And then by combining the light from these two telescopes in coherent way, in phase, you can get the diffraction limit of lambda over d, where d is now the separation. So this separation can be very large, can be 100 meters, 200 meters. And so the light collecting power of the telescope is still defined by the diameter and the total collecting area of the telescopes individually. But the diffraction limit, or the finer details you can see, is now defined by the separation of the telescopes, not the diameter of the individual telescope. And this is what is shown here. Some object which is without any adaptive optics and without any interferometry looks like this. You don't see much details. But when adaptive optics is used, you can actually collapse the details. The central part becomes much more better defined. But you see a little elongation here. You don't know what it is. And then when you remember the 4 telescopes which I showed in Chile, if you do interferometry with those 4 telescopes, called VLTI, Very Large Telescope Interferometer, you can see this. Actually, you zoom into this region, you actually see that there are multiple objects there. And you can resolve them all independently. And that is the finest resolution you can get. And this is what is called a very large array in the US, 27 dishes, each of 25 meters in diameter. And you can combine the light coming from each of these dishes, and you can move these dishes on rails to adjust their separation and thereby the angular resolution. Even more ambitious and challenging, you have this array of telescopes in the US and then an array of telescopes around the world. And you can look at the same target from around the world with these multiple telescopes distributed all the way across the world, and then bring them back together and combine them with very high time synchronization and in very, very accurate phase coherence, and get the baseline corresponding to the separation of these intercontinental distances. This is called very large baseline array, VLBA, and very large baseline interferometry. It's a technology which people use. Radio telescopes around the world look at the same target with high time measurement precision, bring the data together, combine them, and then get the resolution corresponding to the separation of telescopes across the globe. That's also a very common application in astronomy nowadays. Now, in radio astronomy, where are we going next? This is just a slide which shows the next generation radio telescope, which is called the Square Kilometer Array. I hope the video plays. Just give me a moment, watch through the radio. This is called the radio telescope of the 21st century. And I'll tell you why, and you'll see in a moment why it is called the telescope of the 21st century. You're driving toward the telescope here. As I said, this is not a single telescope. It's an array of large number of telescopes. And the light from, or the radio wave from each of those telescopes are going to be brought together electronically and combined together. So these are the array of telescopes. You can see individual radio dishes. And if you zoom out, you can see a really big swarm of telescopes. You can see huge area covered with a large number of telescopes. And then these telescopes are well separated. Their lambda over d is different compared to this area where they are closer. And in the middle, they are much more closer packed so that you can measure all angular scales. And in the middle, there is a very different type of telescope called an electronically steerable array. But you can see this area, right? It's a huge area where large number of arrays. And then around the central part, there are these arms which are radiating out. And each of those arms, we will see in a moment as we move around. Anyway, this one is showing how the electronical steering is going to happen. You zoom into one of those arrays and you'll see how this individual dipoles and how that will allow electronic steering. And then this is how the radio waves are combined together electronically to form the effect of a very large array. Now let us try to zoom out further and see the size of the telescope really. I told you there are these side arrays. So this is one of them. This is 23 kilometers away, 40 kilometers away, 60 kilometers away, 70 kilometers. You keep an eye on this, the dial here. This is a single telescope called square kilometers array. It's 600 kilometers. Now it's 1,000 kilometers away. There is a patch of the telescope, 3,000 kilometers away. So one radio telescope, which is spread out over an area which is 3,000 kilometers across. And there are many dishes in each of them, thereby producing an enormous radio array. Now, what happens eventually is this telescope is so large that half of it is going to be situated in Australia and half of it is going to be situated in South Africa. It's so enormous that you need 2 continents to contain that telescope. That is where the future of instruments in astronomy is heading to. Now, I'll skip some of these slides because I've really run out of time, so I don't want to spend time on this, except for the last one. I think Durgesh will probably talk to you about tomorrow about the solar ultraviolet imaging telescope, so I'll skip through that. The final one I want to talk is the last few slides is what India is currently involved in. I mentioned the 30-meter telescope earlier, which is one of the 3 upcoming very large facilities. So India is part of 30-meter telescope observatory program. It is led by ARIES, Indian in Nainital. Professor Ram Sagar was spearheading that activity when we initiated that effort in India. Then Indian Institute of Astrophysics and IUCAA and many other institutions in India like TIFR and CDAC and so on. Many institutions are collaborating together to realize India's participation in this 30-meter telescope. As I said, it's an international observatory, most probably going to come up in Hawaii. We are not certain yet, but hopefully in Hawaii. This is what it will look like. And this is the inard of the real telescope. You can see this diameter is 30 meters in size, made of hexagonal segments, about 500 of them. Light comes from the top, reflects off this primary mirror, goes to the secondary mirror here, and reflects off the secondary mirror, and then fall on the tertiary mirror, and then go into individual instruments like spectrographs, cameras, images, etc. Now, the observatory is being built by a consortium of institutions in Canada, in China, in India, in Japan, and in the USA. So different parts of this observatory is built by institutions and industries in these various countries. So let me highlight what India is doing. And this is not the entire thing, but at least one major contribution from India. So this gray thing at the top here is one of the segments. I told you the telescope primary mirror is made of 500 hexagonal shaped segments. So this is one of them, looked at kind of from the bottom side of it. And this is an entire support structure which supports this primary mirror. So one primary mirror segment, one of the 500 pieces, and the support structure underneath it. So India is going to make what are called these edge sensors. for the primary mirror. The sensors which senses any tiny misalignment, like at 20 nanometer level, 10 nanometer level misalignment between these segments, these 500 segments, and then produce signals which allow you to measure those tiny misalignments so that the mirror surface can be maintained to the required shape. Those sensors are all being made in India. And then there are these actuators which correct the position. When the sensor sense any misalignment between the relative positions of the primary mirror segments, the actuators chip in and correct for those positions. So those actuators are all being made in India. This entire optomechanical support assembly of each of those segments and for all the segments are being made in India. And it is also making some of the primary mirror segments. Out of the 500 segments, about 100 of those segments are going to be manufactured in India. So this is going to be an enormous challenge. There are many other things India is contributing, but that's just a glimpse. But just to give you an idea of what the challenge is, you can see this is a 30-meter diameter aperture telescope, and you can see made of 500 pieces. I told you these individual pieces have to be aligned with each other to the level of 20 nanometers or better. And you saw that this telescope is just not going to sit there and pointing up in a fixed orientation. Like the animation I had shown you before, the telescope has to point at different parts of the sky, track objects in the sky. In all those conditions, the shape of the surface, it's a hyperboloid surface, the shape of the surface has to be maintained precisely to better than a fraction of the wavelength, like 10 nanometers precision. So this 30-meter diameter surface made of about 500 pieces has to be continuously aligned with each other so that the surface maintains its shape to 10 nanometer or 20 nanometer precision under all the disturbing conditions like the wind, temperature, gravity, any of those disturbing conditions you need to maintain, and also the tracking and pointing of the telescope. So every gamut of pieces of gamut under the telescope which senses the misalignment, corrects for it, etc., etc., the electronics which does that, all that is being built in India. That's India's contribution mainly. I will skip through the details of this. Now, why do we do all this? I explained earlier that, one of the things we want to achieve is to look for presence of life elsewhere. So if you have a star here, not a sun, but some other star, you have a planet there, you want to observe this planet and try to find out, measure the elemental content of the atmosphere of that planet and see if there are signatures, biosignatures or biomarkers, like the kind of life we have on Earth. Do we see those kind of life and the biomarkers corresponding to them in those planets? And to make that happen, you need not only this enormous light collecting capability, you need to be able to block the light of the star. You need to be able to do adaptive optics so that this angular separation could be, this size is 1 arcsecond, and for an 8-meter telescope, this is barely seeable. So you want to get in as close as this at the center of the star where the planets may be. And that is possible only with high-tech adaptive optics and the detection of planets and the measurement of their atmosphere contents. So all in all, we believe that our universe, as I said earlier, that 4,000 megaparsec size universe, visible universe, looks something like this. They are made of many galaxies. Of course, they are made of stars. Stars reside in galaxies, and individual galaxies reside in clusters of galaxies, and clusters of galaxies reside in superclusters of galaxies, and the superclusters of galaxies align themselves in this filamentary structure in the universe. So if you take a snapshot of what is the matter content, visible matter content of the universe, it will look something like this. Each of these points here could be a large cluster of galaxies. and those galaxies then align them into these filamentary structures. There are large areas in there which has no material in there. It's complete void. So it looks almost like a sponge. The sponge is very little matter interconnecting thing, and most of it is actually empty space. That's what we believe our universe looks like today. The main problem is all that structure we saw in there is constituting to only less than 4% of the total matter in the universe. We believe that 22% of the matter in the universe, we don't know what it is, so we just call it dark matter. 75% of the total energy of the universe, I mean, energy and matter are interchangeable except for certain way in which they interact with each other and how it influence other matter. But 74% of the total energy content, we don't know what it is, and we call it dark energy. So total 96% or more of the content of our universe, we don't know. So we can be very proud that we have come a long way from Galilean times, that small telescope which Galileo used 400 years ago to look at the sky. But we haven't come very far. The questions that we need to answer are more today, or even more today, than maybe we could think of 400 years ago. So there are enormous unknowns out there. So the future is really astonishing. Large number of huge facilities coming up around the world, both observing from ground, these large telescopes, observing from space, and they are all going to really tackle some of these fundamental questions, and they are going to hopefully find answers to some of the most really fundamental questions you can ask. For example, how and when did this universe come into being? How did we come into existence? What was the origin of this universe? That was one. How did galaxies take birth and evolve into the variety of shapes we see them today? The spherical galaxies, the elliptical galaxies, and all kinds of intermediate and different kinds of galaxies. How did they all come into the way we see them today? What is the overall large-scale structure of this universe? We think it's all made of that spongy structure of galactic filament. But is that real? Or are there structure which we don't understand? What dark matter? Is there stuff we can't see? And if so, how much? Is it 22% really, or 96% really? Is something else? What is this made of? Is there life anywhere else in this universe? That's an enormous question you can ask, and so on and so forth. Black holes is another paradigm, gravitational waves. Black holes and neutron stars, how they produce gravitational waves and what they tell us about the universe. Enormous possibilities with which you can explore the world we live in. All of these are going to produce huge amount of data, unprecedentedly large amount of data, and that data is going to overwhelm us as we move forward. And there's a huge opportunity for simulation, the data mining, deep learning, artificial intelligence. Nobody is going to be able to look at each individual image produced by a telescope, each individual set of data produced by the square kilometer array. There are going to be petabytes of data being produced over a year, and nobody is going to look at them individually. So they are all going to end up in this huge data mine from which physical understanding of the world has to be derived through data-intensive processes, and that's another huge challenge. So let me stop there. I tried to give you a glimpse of what astronomers try to do with the tools they have, how those tools work. The main tool is a telescope, and two aspects: the brightness, how bright or faint you can see, and how fine details you can see. And then I try to impress upon you what are the limitations of this, both from natural limitations or the fundamental limitations and the technological limitations, and also try to give you a glimpse of how astronomers overcome those limitations by building larger telescopes, by using adaptive optics techniques, by using interferometry, by going to outer space, and so on and so forth. and try to summarize by posing some of those fundamental questions, how we are in a golden age of astronomy, where youngsters who are hopefully in this audience would be making those discoveries you couldn't even imagine so far. Thank you very much.
Thank you, Ram Prakash. And I think the floor is now open for questions. So if you have any question, any one of you, you can raise your hand, or you can mute your mic and ask it directly in the chat box, whatever way you prefer.
I don't see any questions, so I hope people did hear me.
Yeah, it was audible clearly. I think either somebody is please feel free to ask even verbally. Yeah, there is one question from Shirshanundi. So what exactly measures a square kilometer in SKA? Why is it named so, even if its arms are spread across thousands of kilometers?
Yeah, so that is just a nomenclature. Let's not really be worried about the exact term square kilometer. It is just telling us that the total light collecting area, if you add up the light collecting area of the individual telescopes, it will add up to several square kilometers. So if you take a telescope of diameter d or radius r, pi r squared is that area, but now you add up the area of all those individual radio dishes, it'll add up to several square kilometers. So enormous telescope. That's what it's trying to capture. I'm pretty sure the name will change eventually, but this is just the name which it has currently.
Yes. So next question is to theoretically treat a turbulent medium.
Yes, that's a very, very interesting subject in itself. A lot of work was initiated long ago, decades ago, in fact, maybe 10 or 20 decades ago, 10 or 20 years ago, by people like Kolmogorov, people like von Karman, and they came up with methods of quantifying turbulence and also methods of understanding the effect of the turbulence in light passing through them, and so on and so forth. So there's a whole lot of literature out there in understanding turbulence theory and its effect and various contexts. I'm just right now talking about turbulence in our atmosphere, but turbulence is a very, very vast medium and a very vast topic, and huge lot of literature out there. But as far as atmosphere is concerned, and its quantification of turbulence and its impact on in the image quality, etc., there are many stalwarts like Kolmogorov, von Karman, who studied wind and wind effects, and then Knoll. There are quite a few names which come to my mind in this specific area of turbulence. There's another question about explain briefly what is signal to noise ratio. Signal is what we are trying to measure, and the ratio of the signal above the uncertainty in your measurement, any kind of noise uncertainty, that is quantified as signal to noise ratio. So signal is a numerator, and the measurement uncertainty, any measurement has some uncertainty. And in this specific case, I try to explain what is the uncertainty coming from the inherent nature of photons, called the photon noise. And that uncertainty as the quantitative relation that if you collect n photons from any source and repeat that experiment multiple times, I collect n photons today, I collect n photons tomorrow, I collect n photons, repeat that experiment multiple times, Every time you will not get the same number or mean brightness of that object, but the spread you will find that it goes like root n. So it's Poisson in statistics, basically. The photon counting process is determined by Poisson in statistics. And then, but this SNR is a term which is not limited to photon counting. In any measurement, you have a signal and you have an error or uncertainty in your measurement. The signal over the uncertainty is the signal to noise ratio. Is that clear? I hope so.
Yeah. And then question on whether one day work to collect multi-wavelength data in future.
Yeah, already telescopes do collect multi-wavelength data, but it's not like a same telescope can collect radio light as well as radio wavelengths as well as X-rays. That will be difficult. But any so-called optical telescope does collect light in infrared, optical, UV, etc., etc. But if you want to collect radio wavelengths, your technology changes. The kind of detectors which are sensitive to radio waves, for example, radio waves may pass through a glass. The glass cannot be reflective to certain radio waves. Then you need a metallic reflector for radio waves to be reflected. So these kind of technology differences are there. Therefore, if the wavelength range is very different technologies are required for collecting light. And the way you collect and focus light in X-rays is very different from the way you collect and focus light in visible wavelength. So the technology is different. So that means that a very widely ranging wavelengths, you need different technologies. But for all relatively close by wavelengths, you can use the same technology and same kind of telescopes and detectors. So
The question is, can just by building a telescope on the moon, will you really solve the problem of seeing?
yes and no. Yes, it will solve the problem of seeing, but no, because without most probably the telescope will be destroyed by something which is bombarding on the surface of the moon. The moon is not protected by an atmosphere like that in Earth. So there is a high chance of something hitting the telescope and destroying it. But yes, in principle, yes, but you don't have to go to the moon. You can just go a few hundred kilometers from the Earth surface, and the atmosphere is thin enough there. Maybe you go to 500 kilometers away, 600 kilometers away, or few thousands of kilometers away, and you can you can put your satellite there and observe. So you don't necessarily have to go to the moon.
Yeah, I think
anything above the atmosphere is good enough.
Viru has raised his hand to ask a question. Yeah, Viru, please.
Yeah. Hi. So I think nice talk. The only thing I have is a kind of a reaction from you. As you said that this is a kind of a golden age of astronomy in India, because a lot of the mega science projects as well as a lot of other initiatives are coming up, and it actually requires a lot of hands-on instrumentation, and people should be involved, and especially from us, say the IIT, I think it should be. But on the other hand, we are seeing that students are not going away from doing anything hands-on. They like to do simulations, data analysis. They are very much interested because it's also very exciting because they get immediate, kind of results and satisfaction by publishing papers and other things. But I mean, how to capture these young minds and into something which is so pristine and very much required, at least in this next few decades to come, because it's really a enormous opportunity and unique situation in India.
Mm-hmm.
So if you can just comment on that, because that's from our side also, we would like to know and help, and also the students who are listening, some of them may have interest, but because of this kind of a little bit of a lag and more time is required, they may not be so much enthusiastic to pursue what they like.
Yes, so I think there are various factors influencing this. Till recently in India, the opportunities were less. If you want to be an astronomer as well as a cutting edge engineer, the opportunity was very few. I mean, you could work, but we are not building facilities in large numbers. We are not involved in international programs. That scene is changing now. So the opportunities are becoming available. Now India is part of TMT, India is part of SKA, and India has launched AstroSat recently. India is going to launch a mission to study the sun, Aditya. And I think there are probably about 20 astronomy-related missions in pipeline for ISRO coming up over the next 10 years or so. And this is an enormous opportunity. And these are all going to be built by engineers. So the opportunity landscape has changed. So now it is our job to take that message to people saying, look, here are opportunities. Things were different 10 years ago. When you were beginning to get into education, things were different, but now it is your golden chance. You can be an astronomer and you can be contributing to building these facilities because you know how to make things, and that is important. And some of these challenges. So the second thing is a challenge. So if the challenge is boring or it's not challenging enough, it's very hard to attract people. Now, places like IITs and many good universities, there are students who like a good challenge. And so with these international and large ambitious programs, national and international ambitious programs are offering those challenges now. And that will lead to publications. It's not like a run-of-the-mill job you do. You take an IIT degree, go to some place, maybe few of people end up understanding how to make robots communicate with human beings and whatever, right? But most of the rest of the people end up writing insurance software, right? Banking software. And they get bored. At the first 5 years into the job, you're bored. You don't know what to do after that, but you're trapped. So now these opportunities are opening up and the challenges are good. So at least a few of the people who really like a challenge to tackle, the challenges are such that it's an equivalent to the physics equivalent of trying to quantize gravity, right? You are at the frontier. You're really taking on the big questions. Imagine how you have a 30-meter diameter surface made of 500 individual glass pieces. At the scale of a few centimeters across the surface, you have to maintain its shape to 20 nanometers. And this is not a lab experiment. This is sitting on a mountain half the height of Mount Everest, right? And all kinds of problems out there. So what more challenges can, and then the questions you can tackle are some of the most fundamental questions you can tackle. So this message, once we try to spread, my fear is there will be many more people trying to get into the field than we can accommodate in terms of the job positions we have, in terms of opportunities, in terms of placements we have, etc. I think the tide has turned now where it's no more the interest in students or aspirants which is limiting. It is their concern about, will I get a job, that is going to limit. And that's something which we need to solve. I mean, I'm very happy to see IIT Indore as an astronomy department coming up. We need many of them. We need placements for these aspirants who can find jobs and tackle these problems. That I think that is the next round of challenge. The challenge is no more really interesting people. I mean, we have to still continue taking that message to people that opportunities exist, challenges exist. But people are beginning to realize it. But their main worry is, okay, here is a campus interview from Apple, or is a campus interview from Microsoft. with a guaranteed job, but I will tweak Windows 10 to Windows 10.1. That's going to be the life I'm going to have, right? Or do you want to figure out whether there is life in that star, right? And the planet around that star.
Right.
That's a challenge, but they then worry, oh, if I try to tackle that problem, will I get a job? Do we have enough positions? That's where the challenge is.
Absolutely correct. Yeah.
Yeah.
Thanks a lot. Yeah.
Thanks.
Thank you very much
Amit,
for giving me the opportunity to speak to this audience, and it's my pleasure. And I'll be happy to do that again. Thank you.
Yeah, sure. Definitely.
I think if you have a few minutes, Amit probably has a question. His hand is still raised. Sorry to bother you. Yeah. Amit, please
No
go
problem.
ahead.
Hello,
I have one technical question. You showed this one of these stars which is covered by the coronagraph. I'm just curious where this coronagraph is mounted in the telescope.
Yeah, there are various ways of doing it. One, for example, in the Aditya mission, Aditya L1 mission, they want to look at the corona of the sun. So what they do is to make an optical arrangement where the mirror has a central hole. The primary mirror has a central hole so that the light from the disk of the sun just does not reach anywhere. You collect light only from the corona. So that's just a simple way of doing it. The other way of doing it could be by interferometric nulling. You apodize the light and then null the light from the star while you don't null the light from the planets around it. So you can. So there are various ways of doing it, or you could just put a disk in front of it which blocks the light from the star. Right. Now the challenge is if you want to detect the light from a planet around a star, let's say a distant star, and measure elements in its atmosphere, direct element measurement. Indirect, there are possible ways even now, but direct measurements, then you have to kill the light of the star with a factor of 1 billion or more at an angular separation which is a few lambda over d. So where d is 10 meters or 15 meters in diameter. If you look at a star at 1 micron wavelength with a telescope of 15 or 20 meters in diameter, the lambda over d is going to be very tiny. Right? With a half micron, with a 10-meter telescope, the lambda over d was 0.01 arc seconds. So if your d is now 20 meters, the lambda over d is much smaller. At small separations of 1 or 2 lambda over d, the light from the star and its scattering has to be suppressed by a few factors of billion. BILION. It's not million, it's billion. That is a huge challenge in designing a coronagraph.
Thank you very much for
Thanks.
your time. Yeah, thanks. So I would request participants, if they have any further questions, probably they can email directly to Professor Ram Prakash. Will that be okay to you, Professor?
Yeah, I'm sure.
Okay.
Maybe even better would be you could collate them if you have. I'm happy to answer them, but if the questions are collated together, it might be easier for me to answer them.
Yeah, if we what we will try to do, we will probably create a Google Doc and people can post their questions there.
That's the best way to do that. Yes.
Yeah, and then share it with you.
Okay.
Okay. Thank you very much for your
Thank
time,
you.
and let us thank all the speakers of the day. Thank you.
Thank you. Bye-bye.
Bye.
Thank you.